Good morning, everyone. It's so wonderful to have all of you here this morning. My name is Gopal, and I'm a physician scientist here at the Broad Institute of MIT and Harvard. I know that a number of you have been able to join us earlier in this week for a couple of the tutorials, but I think the majority of you will be here for the first time. So I wanted to take a few minutes to say a few words about the vision behind this workshop. You know, I introduced the sessions the last 2 days by talking about the need for mission and safety critical systems and giving you some perspective from the life sciences. I wanted to actually this morning tell you a bit more of a personal story about how I came to these topics as somebody that doesn't directly work in the field. I had an amazing opportunity as a graduate student in physics to do theoretical work embedded in an experimental physics group, and moreover, to work alongside an incredibly talented group of pure mathematicians. And one of the key experiences that I had, kind of independent of the actual technical skills that I learned, was that I saw that even though the work of our pure mathematician colleagues tended to take place in parallel to the work that we were doing on the theoretical physics side, there were these key moments where the mathematicians were able to make fundamental advances that I think would have been beyond the reach of some of the traditional techniques of theoretical physics. And moreover, these moments tended to happen in these kind of punctuated equilibrium type situations, and it wasn't so much of a sustained impact. But the only reason this happened was that our field had leadership that valued this long-term sustained relationship. Moreover, as a physicist, I had made extensive use of computer algebra, and it was totally by chance that I encountered these very different types of software systems called interactive theorem provers. And as a final year graduate student, I just as a hobby decided at some point to download a theorem prover called Isabelle and play around with some basic tutorials. I proved that if you reversed a list twice, you got back your original list. I showed that the square root of 2 was irrational. And this really didn't have a whole lot of impact on my work, but it was an experience that I filed away in the back of my head. Ultimately, I entered industry to work as a data scientist and then software engineer, and ultimately trained in medicine, which is what brought me here today to the Broad Institute, where I have a unique role that allows me to take a bird's eye view of our organization, as well as think about the life sciences and medicine as a field and how to build the emerging interface with machine learning. Now, our perspective at the Broad Institute comes from our long history in the genomic space. We've known for several years now that the growth of global genomic data production is exponential, faster than Moore's law even. As I've mentioned before, there was an interesting paper written a couple of years ago called Big Data, Astronomical or Genomical, where the author predicts that by the year 2025, the volume of genomic data production is going to exceed that of astrophysics and even social media. Now, for those of you in the life sciences, you know that it's not just genomics that's seeing an exponential growth of data production. There are many other interrogation and measurement modalities as well, from single-cell RNA sequencing to CRISPR-based assays, to cellular imaging, to an entire spectrum of medical imaging modalities. Now, from my perspective, the net result of this exponential growth of multimodal data production will be that in the next decade, we will see the life sciences and medicine become key drivers of progress in machine learning and AI, and moreover, give rise to an entire ecosystem of software products, some of which will have to be mission and safety critical. And when I started to think about this, I came back to the experiences that I saw in graduate school, in this incredible, diverse group of theoretical physicists, experimental physicists, and pure mathematicians working side by side. And as I said earlier, the impact of the highly rigorous techniques of pure mathematics on our field wasn't a sustained one, but it only happened because of visionary leadership that valued building those connections well in advance of the techniques actually being necessary, and building a culture that allowed this interface to really deliver real-world impact. My perspective working on strategy and operations full-time is a similar one, which is that in the future, we will need mission and safety critical systems, but they're not going to be built overnight when we need them. We have to cultivate these relationships well in advance. And so a couple years ago, I approached my friend Jimmy Koppel, who works in the adjacent field of programming language theory. And we started kicking around some ideas, and we put together a really diverse program committee with people from mathematics, from programming languages, from compilers and formal methods. And we decided actually to take a step back and set aside the life sciences or medicine or really any other domain and simply ask some very broad questions about how one builds highly reliable software in general. What are the tools and techniques that are available? And when you need to implement them, what is the overhead? And so by making this workshop domain agnostic, what I think we're really hoping to do is to start a conversation. We know that whether it's 3, 5, or 10 years from now, when we need these systems, by getting an early start on bridging these unlikely communities, we'll ultimately be able to connect the right people to the right problems. Now, I'm the first to admit, as I've said before, that the vast majority of you are unlikely to leave this workshop doing formal proofs left and right, and that's totally okay, it's by design. But I hope what we will have accomplished is to plant some key intellectual seeds, stimulated some curiosity, and most importantly, maybe jump-started some important relationships so that over the coming years and decades, we'll be able to tackle some incredibly ambitious problems that I think will be of great consequence to our society as a whole. So with that, thank you again for being here this morning. I'm going to turn it over now to my colleague, Gregory Malecha, who'll be introducing our keynote speaker.
First speaker today is Professor Kathleen Fisher from Tufts University. Professor Fisher has been a really big contributor to an advocate for formal methods in the community as a whole. She served as a DARPA program manager, where she started the Hack'ems program to build unhackable software, and also does research advancing the state of the art in verification. Beyond formal methods, she's an ACM and Hertz Foundation Fellow and a co-chair of the Computing Research Association Committee on the Status of Women. Her talk today is about the using formal methods to eliminate exploitable bugs, which is a great topic. We have a lot of bugs in the world. So Kathleen, are you all set?
I am here, yeah.
Great. All right, I'll turn it over to you.
Cool. So thank you for that setting the context and for the really gracious introduction. I'm going to talk about, as Gregory said, using formal methods to eliminate exploitable bugs. So I want to start with the observation that network computers these days are really unacceptably insecure. And to kind of drive that home, I want to talk about a specific example of an automobile. And to do that even more, I want to put you in the seat, the driver's seat, as it were, of an automobile that actually happened to a reporter from Wired magazine, Adam Greenberg. So I invite you to close your eyes and imagine that you are driving this white Jeep Cherokee down Interstate 64, just outside of St. Louis, Missouri. And you're on the highway and you are approaching an overpass. It's a normal day, normal traffic on the highway. And as you start to go up the overpass, all of a sudden the air conditioner just starts to blast cold air. Your hands were on the steering wheel. You did not touch your air conditioner at all. And then as you're kind of puzzling over why your car decided to blast the air conditioner, the radio comes on and the radio starts to blast Skilo music. And when you go and push the power button and the volume, nothing happens. It continues to play Skilo at top volume. And as you're noodling over that, the windshield wipers come on and the fluid starts coming up to clean the windshield wipers. So now your windshield is obscured and you can't see very well what's in front of you. And you're going up the overpass as all this is happening and your transmission cuts out. So now when you push down the gas pedal, the engine revs, but your car no longer starts to pick up speed. In fact, it starts to slow down because you're going up the overpass and cars around you start to honk at you, and you look in your rearview mirror and you can see a semi-truck coming up from behind you, picking up speed. And you hope very much that the semi-truck notices that you are no longer going at the speed limit, you are slowing down. So that actually happened to Andy Greenberg, the reporter from Wired magazine that I described earlier. He wasn't completely taken aback by all of these things happening because he knew that the Jeep Cherokee that he was in had been hacked by white hat hackers, Charlie Miller and Chris Falachek, as an example of what could be done with a modern automobile. So to understand why this is possible, let's step back a little bit and talk about what a modern automobile is. So a modern automobile really is a computer on wheels. It's really a networked set of computer on wheels. A typical car these days has somewhere between 30 and 100 embedded control units. An embedded control unit is really just a computer. They vary in size from things that are super small, very specialized computing devices, up to full-blown computers running Linux or Windows operating systems. And they're all connected via CAN buses, but those are just network connections. So they all talk to each other. And in work that preceded Charlie and Chris's work, Stefan Savage from the University of California at San Diego, and Yoshi Kono from the University of Washington showed that they could achieve essentially the same thing with a different car. They showed in a first paper that if they could connect to the diagnostic port that was, oh, you can open your eyes if you had them closed before, it's easier to stay awake. If they could connect to the diagnostic port that was under the steering wheel, and that is in fact required to be on all US cars made after 1996, that they could then reflash or rewrite any of the software in the car. And if they did that, they could control the acceleration, the brakes, basically any of the functionality of the car that was under software control. And pretty much all of the functionality of a modern car is under software control. And that is actually for really good reasons, right? The brakes are under software control. That's what allows us to have anti-lock braking. And anti-lock braking is a really important safety feature. The acceleration is under software control because that's what gives us cruise control, which is also a really nice feature. The fancy cars that will park themselves, that means the steering is under software control. The fact that you have a key fob, when you push the key fob, it unlocks the doors, that means the locks are under software control. More and more of the functionality of a car is under software control because it's the same reason why software is advantageous in all the other domains. It gives the ability to be very flexible and to change and add features post the sort of creation of the hardware features. The reaction to that first paper that Stefan and Yoshi wrote was a little bit muted because to do that, to control all of those things, they were in the car plugged into the diagnostic port under the steering wheel, which meant they were like physically in possession of the car. So they could, hotwire the car and, drive it off already. So what was the big deal? They responded by writing a second paper that showed that they could achieve exactly the same thing without touching the car in 4 different ways. One was by placing a virus on a laptop that was the mechanic's laptop. And then when the mechanic plugged into the diagnostic port, Yoshi and Stefan and their team of graduate students could take over control of the car. They could also achieve the same effect by hacking in through the Bluetooth system, by burning a version of a song on a CD that caused a buffer overflow in the entertainment system of the car. So when you remember CDs, kind of ancient technology, when you put the CD in the car, it would, again, allow them to take over control of the car. And then finally, through the telematics system. So telematics is the term for the thing like Uconnect, or like each vendor has their own brand name for this kind of service, but it's the thing that if you get in an accident, arranges to call 911 or to have somebody come help you. It's the thing that if you lock your keys in the car, they can arrange to remotely unlock your car. That service means your car has a cell phone number, and that people can remotely call that cell phone number and connect to your car and talk to it at the same way that 2 computers can talk to each other. So what Yoshi and Stefan showed was that they could call the car that they were working on and hack in and take over control of the car that they were hacking into. And that's exactly the same approach that Charlie and Chris took with the Jeep in St. Louis, where they used the cell phone interface to hack in and remotely take over control of a car. And that's particularly scary because the cell phone network works all over the world, right? So you could hack into these cars anywhere on the planet and take over control. So that attack caused the recall of 1.4 million cars and caused the automobile industry to take software security slightly more seriously than they had before. So, you're sort of like, why are these things so insecure? And of course, I'm just talking about cars, but there are many, many other computer systems and computer systems that affect the real world. Things like pacemakers and insulin pumps and the doors to prison cells that are now connected to computers and controlled by software that is connected to, that is connected via networks to other computers. Why are all these things so insecure? And the answer to that is that security is a super hard problem. You have to get like everything right to get security to work right. If you get anything wrong, the attacker has a way to get in. And there's just lots and lots of things you have to get right. You have to get the design right in the first place. You have to write down a specification that's correct. you have to have programmers who then implement that specification correctly. You have to make sure that there aren't side channel leaks that are leaking out information that you don't want to have leaked. You need to have the system configured properly. Your users have to use the system properly. They have to use passwords that are not easy to guess. They have to not be spoofed or fooled by increasingly clever phishing attacks that go after, that get them to give away their credentials. You have malicious insiders, you have hardware attacks, you have like physical security attacks, so attackers could actually go up and change the software running on the system. You often use third-party software. So all of the things that you have to get right about your software, somebody else has to get right about their software too. So that, you know, there's just a lot of things that have to go right. In this talk, I'm just going to talk about one of these dimensions, implementation errors, and a technique, formal methods that can really help make implementation errors much less impactful for security purposes. Okay, so I've said, you know, security has many, many aspects, and that's why the octopus is there, because the octopus, even with 8 arms, doesn't have enough arms to really fully take care of all of the problems. I would argue that implementation errors are a really key part of the problem. And one of the reasons for that is because there are many exploitable vulnerabilities. So a vulnerability is just a bug in software. It may or may not be a problem. An exploitable vulnerability is a bug in software that an adversary can take advantage of to either take over remote control of a system or to exfiltrate information. So this chart shows data about how many vulnerabilities are actually exploitable. And it often takes a lot of cleverness on the part of hackers to convert a bug into something that is an exploit that can exfiltrate information or take over control. So this chart is from 2018. It shows data from the midpoint of the year. The horizontal axis is the number of vulnerabilities, is just a number of vulnerabilities. And the vertical classification is what we know about those vulnerabilities. So unknown is we don't know if there's an exploit or not. Public exploit means there is an exploit that corresponds to this vulnerability that is published. It's out there in the wild. Private means we know there's an exploit, but it's not been published. Only the people who created it know that it exists, except that the people who created the data know that it exists as well. And then public proof of concept note means that there's been publicized enough information that shows that like there's a way to exploit it, but the actual exploit has not been published. And what's relevant about this data is that of the close to a little bit more than 10.5 thousand vulnerabilities that were reported in the first half of 2018, almost half of them had exploits. So what the data shows is that although it's quite challenging to convert a vulnerability into an exploit, it's done with with frequency, right? Almost half of the time in these reported vulnerabilities. Then vulnerabilities, exploits cause real damage that we really, really don't want to happen. So we saw that with the car examples, but there are many, many other examples. This slide just shows 2 more. The 2 kinds of main threats are remote code execution and exfiltration of information. So the first one, the Microsoft Security Bulletin MS-15078 critical, is an example of remote code execution. It was reported by Microsoft in 2015. It's an old example just because when I originally put these slides together, that was when I was putting them together. It's not like there haven't been more of these in the future. What's notable about this is it was caused by a buffer underflow. So this is a bug in the code, and it affected every single Windows platform that Microsoft supported at the time. And an attacker could use it to take take control over a device and cause it to do whatever the attacker wanted to do. The other attack that I wanted to highlight is Heartbleed. It was also caused by a bug in the software. In this case, it was a missing bounds check in the OpenSSL, which is a common library. This attack allowed an attacker to exfiltrate information, so steal things like secret names, usernames, secret keys, usernames, passwords, basically anything they wanted to. And it would steal this information without leaving any kind of a log that they had been in the system. So you couldn't tell that your information had been stolen. So that's bad. But as I mentioned before, it's actually quite challenging to convert a bug into an exploit. Most hackers are not good enough to be able to convert an arbitrary bug into an exploit. But there are entrepreneurial hackers who are good enough to find these vulnerabilities and then package them up in exploit kits. So the Phoenix exploit kit, for example, was created in 2010. It combined a whole bunch of these exploits that are related to, that are bugs basically that have been converted into exploits, and published them or offered them up for sale on the dark web, so that anybody who could find the dark web and who had money could buy this kit and then could do the exfiltration and remote hacking just by being able to find the website and pay the money. So this enables these kinds of remote attacks at scale without having to have nearly the same level of expertise. So that's bad. Right. So this kind of topic of the talk is, this is bad. We need to do something. What are we going to do? So one of the hypotheses is that formal methods can eliminate many of these exploitable vulnerabilities. And if you've been paying attention to formal methods research, your first response might be like, yeah, I've been there, I've heard that, I've tried that, I wasn't impressed, right? Formal methods research, formal methods is a really, really old research area. It started in like the 1950s, 1960s, back in the dawn of computer science. People have been working on formal verification of software even when we started writing programs. This has been on the research agenda of computer scientists since the beginning of computer science. And for most of the history of computer science, they've pretty much failed miserably. What they've been able to verify has not been very impressive. What I argued to DARPA is that now is a really good time to revisit that hypothesis. And so these next few slides talk about why is now a good time. And the first answer is faster hardware and more resources. It turns out that formal methods like machine learning is largely a search problem, where you have this vast space and you want to find a proof that your system is doing what it's supposed to. And search problems benefit tremendously by having faster computers and more memory. So the fact that our colleagues who work in hardware design have been making us faster and faster computers following Moore's law and designing bigger and bigger memories for 40 years have made it so that formal methods are able to be much more effective without the formal methods researchers having to do anything. So that's one key change. Another key change is automation. So originally, formal methods techniques meant that formal methods researchers had to do everything by hand. But over time, automation has become a much more important part of formal methods so that the computers do more of the work. So that's captured, some of that intuition is captured on this slide. And what this slide is reporting is results of the SAT solver competition. So what is SAT solving? SAT is satisfiability. It is the problem of given a Boolean formula. So that's a formula where the variables stand for Boolean, so true and false, connected with and, or, and not. You want to come up with a truth assignment of true and false to those variables that makes the whole formula true. That problem is NP complete in general, which means the only guaranteed way of coming up with an answer is to try all possible assignments of true and false to those variables, which takes exponential time. Is the only way we know how to solve the problem right now, for sure. But it turns out that this problem is very, very amenable to heuristic-based solutions. And so for the past 20 years, there's been a cottage industry of researchers coming up with more and more and better heuristics for solving this problem. And it's very valuable to have heuristics to solve this problem, because although it sounds like very, very theoretical and not very useful, it turns out you can code many really interesting questions about software into humongous, ginormous Boolean SAT formulas, and then ask questions about the software by asking a SAT solver to answer questions about that Boolean formula. So what this graph is doing is showing that Daniel Lebert and colleagues took so there's a competition every year that people all over the world enter their SAT solver to show, to compete against the rest of the world about how good their solver is. So Daniel Lebert took all of the winning competition solvers from 2002 to 2010, and he ported them to a 2009 machine, and he ran them on the 2009 benchmark programs. And then he plotted how long did it take them to solve each problem. So each shape in the graph is a particular solver. Each point is at what time did it solve that particular problem. So the horizontal axis here is the number of problems solved, and the vertical axis is how long it took to solve that particular problem. So this dot over here is that the solver MinSat or Ling Lang took 160, it solved problem number 160 at time 590. And one key way to see the significance of this data is like, look at problem point 80. And the best time is dropped from 10,000 seconds, sorry, not 10,000, 1,000 seconds in 2002 to 40 seconds in 2010. So 2 orders of magnitude improvement. And that's because they're all running on the same computer. That's on top of the improvements that the hardware designers have given us. So this automation and improvements in automation have made a big difference. And then a third huge change is more infrastructure. So in the beginning, and for most of the history of machine learning, sorry, not machine learning, formal methods, the people who did the research in formal methods then applied the formal methods techniques to whatever verification application area they were trying to solve. So they were kind of wearing 2 hats and flipping back and forth between those 2 hats. Research in formal methods, applying that research. And that was kind of too much to ask for one set of researchers. So what's happened now is that there's a whole bunch of formal methods tools that are mature enough and have sufficient tooling and documentation and like textbooks and tutorials on the web, so that now the formal methods researchers can continue to work on advancing the state of the art of those tools, but other researchers who care about the application areas can take those tools and apply them to solving the problem areas. And so basically the infrastructure has advanced to the point where it can be applied by people who are focused on the application areas. There's just a lot more support. And then I would argue that there's one fourth thing, which is the motivation of the application people, the users. The problem complexity has gotten to the point where users, and this is not true across the board, but in certain application areas, users are completely aware of how fragile their software is, how important it is that that software stands up to attack, and how much they need help, how much they can't do it without formal tools, right? Humans are really bad at reasoning about uncommon occurrences, right? A 1 in a million event is something that humans are terrible at thinking about, because a 1 in a million event to us just was never going to happen. It's not worth our brain cycles to think about a 1 in a million event. But for like Amazon Web Services, a 1 in a million event happens like less than every second. And so having tools that help developers drive the system into 1 in a million events is incredibly useful. And so the quote at the bottom of the slide here talks about experience that the developers at Amazon Web Services had in using TLA to model their web services to improve the rigor and the quality of their services so that it would have longer uptimes and have higher levels of quality, which they could then take to financial companies, for example, and encourage those financial companies to use their cloud services. So customers who were very concerned with the quality and the privacy of their data. And then you have a talk coming up about TLA Plus. So that TLA is the system that Amazon Web Services is using in this piece. Okay, so that's the hypothesis about why now would be a good time. And so DARPA bought this argument and invested $70 million in 2011 in trying out this idea. So DARPA is, the mad scientists of the Defense Department. Their job is to take technical risk off the table. So if the argument is like formal methods actually can make a big difference in this problem that's related to national security, but nobody believes it because there's 50 years of history that says formal methods is not up to the challenge. That's exactly the kind of problem that DARPA wants to be thinking about, to say like, yes, okay, we can demonstrate in fact that formal methods is up to the challenge. And so that's what the HACMS program was all about. Let me just take a drink and a breath. So the setup of the HACMS program is the one that I've been outlining for you, that formal methods can yield vehicles that are less susceptible to remote cyber attack. The threat model that we were concerned about was the attacker has no physical access, but they have full knowledge of the system and all the source code. So they know everything that would be reasonable to know about the system, but they can't physically touch the system. So why is that an interesting threat model? Because of course an attacker could physically touch the system. The reason why this was the one we settled on was because if you have to have physical access to the system, well, then you can't scale that much. You can only attack the systems you can actually touch. And any one person or even a group of people can only touch physically so many different systems. But if you can attack a system remotely, and then you can script it and you can attack thousands or hundreds of thousands or millions of systems all at the same time. And that's much more likely to be a national security threat. We also assumed that the hardware was correct. we know that that's a completely bogus assumption, but you have to limit your scope, and you can't attack all problems at once. So for the purposes of HACMs, hardware was assumed to be correct. We had a bunch of experimental platforms, but the two I'm going to focus on right now or today are an Arducopter, which is a quadcopter that you could buy off the shelf from Amazon. It's about roughly 100,000, something like 80,000 to 100,000 lines of code, completely open source. Everybody who was working on the program could see all of the source code associated with the quadcopter. And then Boeing's unmanned Little Bird, which is a helicopter that's big enough to have 2 pilots, but it can also fly completely autonomously. Boeing's unmanned Little Bird is ITAR restricted and proprietary, so only the Boeing engineers could actually access the code. So any effort to apply formal methods to Boeing's unmanned Little Bird had to be via path where the formal methods engineers taught the Boeing aviation engineers what to do, and then the Boeing aviation engineers could actually apply the tools and techniques to the helicopter. Then to get a baseline security assessment, we hired a world-class red team to attack the vehicles as they were at the very beginning of the program and then at the end of each phase. So there were 3 phases. So the red team attacked the vehicles 3 times. The red team didn't get physical access. They had to remotely attack the vehicles. They were able to attack and take over control with surprising ease. Like, we were totally not surprised that they could take over the quadcopter, probably because the designers of the quadcopter were not really concerned about a threat model where attackers would remotely hack in and take over control of the quadcopter. They were probably much more concerned about the threat model that somebody was flying the quadcopter in a park and no one could connect to the quadcopter, and the quadcopter was just flying around the park with no control. The Boeing engineers were a little bit more surprised. They thought that they had done a good job, and they had tried to make it so that an attacker could not take over control. So I'm going to play a video now, hopefully, assuming Zoom willing, that shows not the red team, but one of the blue teams who had gone and looked at hacking tools, and they themselves show how to hack into the quadcopter to give you a feel of like what's involved and how easy it is.
This is an AR drone quadcopter. We'll be using its airframe in our research vehicle in the HACMs project. Eventually, we'll upgrade its control electronics so that we can host the provably secure software that we're developing on the project. But for now, it serves as a convenient platform to demonstrate the kind of security vulnerabilities we're concerned about in HACMs. Even though it is essentially a toy, it illustrates the same sort of vulnerabilities that can be found in many network-enabled cyber-physical systems, including automobiles, SCADA systems, and aircraft.
The AR drone is controlled using standard Wi-Fi technology. It acts as a Wi-Fi access point to which you can connect with a phone, tablet, or PC running the ground station application. AirCrack is a readily available software package for monitoring and injecting traffic onto wireless networks. We will use it to attack the AR drone from this laptop. First, we identify the physical address of the drone access point. Next, we send commands to deauthenticate all clients, including the ground station. The ground station now has no control over the vehicle. The attacker laptop has taken control of the vehicle, and the ground station is not able to reconnect. Finally, we can send arbitrary commands from the attacker laptop. In this case, we will simply cause the vehicle to land.
Even though this was a very straightforward attack, it is representative of some of the current threats to network cyber-physical systems that we will address in the HACMs project.
Right, so you can get a feel of like how easy it was for the red team to hack into the quadcopter. It's a little bit harder to hack into the helicopter, the unmanned Little Bird, but still distressingly easy. So that was the baseline. Then the blue teams, the formal methods researchers, got to work focusing on the SMACM copter, their term for the quadcopter in phase 1. They did a bunch of things. So this kind of horizontal axis is time. So they started with the quadcopter off the shelf. Had a monolithic software stack. It had no real-time operating system. It had no security, which is why it was so easy to hack into. They re-architected the stack. They changed the underlying processor, so it was a little bit more powerful. They then added a free, an RTOS, a real-time operating system. They added a hardware abstraction layer so that the software that was running on top didn't really know if it was running on top of this hardware platform or the hardware platform it was running on before. Then they got to work replacing some of those pieces with formally verified equivalents. So they started working replacing the free RTOS with a verified RTOS developed by Data61, aka NICTA, out of Australia, eCronos. And then they started replacing the RDuPilot software with software that was written in a domain-specific language in Haskell that then generated low-level C code along with proof obligations that could be discharged using formal methods tools to show that the system was memory safe. And over time, they kind of migrated more and more of the system so that it was green and verified as opposed to white and legacy systems. They also developed a high-level model of the overall system that allowed it to prove kind of system-wide properties. And from that high-level model, they generated the glue code that connected all these pieces together, and again, used that to prove system-wide properties. So at the 18-month assessment period where they had to kind of turn over the system to the red team again, they were able to replicate most of the capabilities of the original quadcopter. It had stability control, it had altitude hold, it had directional hold, and denial of service detection, which was actually a new feature. It also had about 80% of the GPS waypoint navigation capability built in. So that was the 20% that was missing was the rest of the GPS waypoint navigation. They proved a bunch of system-wide security properties. The system was memory safe. It ignored malformed messages. It ignored non-authenticated messages, and all good messages that were actually received by the SPACM copter will reach the actual motor controller. The red team found no security flaws in the 6 weeks that they had to try to break the system. So my colleague at DARPA, who was an expert in penetration testing, his assessment was that the SPACM copter at that point was the most secure UAV on the planet, which is kind of scary if you think about what UAVs are doing. My boss at DARPA at the time, his assessment was that this result completely justified the entire $70 million investment in the program. And he told me at this point that they had actually thought that the whole program would fail, that they didn't think that formal methods would be up to even this much of the challenge. And they were delighted that it had succeeded, right? DARPA isn't afraid to take risks. They invested $70 million in something they thought was not going to work. And so they were delighted that it actually did work. Then in the rest of the program, we continued for another 3 years working on, 2.5 years, working on applying the same tools and techniques to the rest of the system. So they applied the same results to the Boeing's unmanned Little Bird, this time working through the Boeing engineers. At the end of the program, they had the red team attack the Boeing unmanned Little Bird while it was in flight with the test pilots. And they had the same results, thankfully, that the red team was not able to disrupt the operation of the quadcopter in any way. So this was like a huge positive result for the quality of the software that resulted by using these formal methods. And the John McCain National Defense Authorization Act, which is the bill that pays for the Defense Department, the one from last year, specifically called out HACMs and asked the Pentagon to investigate using HACMs-based tools in the future. The one from this year also explicitly calls out HACMs and directs the Defense Department to investigate using HACMs tools in the future. The hope is that this demonstration will cause Pentagon procurement officers to write in their call for proposals that defense contractors are required to do this kind of analysis and produce machine check proofs of memory safeness and correctness of certain kinds of properties so that those military systems will also not be hackable to the same standard that these systems were. And that if the defense contractors come back and say, we can't do this, that's ridiculous. If you want the system, you have to take this requirement out, that the Pentagon procurement officer can point to HACMs and say well, the grad students who were working on HACMs were able to do it. Why can't you do it? And leave the requirement in so that then the defense contractors go and build up their capability, hire those grad students or other grad students, build the tooling up in their infrastructure so that they have that capability, so that they develop those systems. And then as that capacity grows, they can apply them to other kinds of systems, things like pacemakers and insulin pumps, other kinds of things where it's a matter of life and death that the software is correct. So that we create a virtuous spiral. We're clearly at the beginning of that spiral, but I'm hopeful that will actually happen.
One short question. So
yes.
the slide mentioned there that by the end, the red team was not able to attack the helicopter. Did they try to do the same at the beginning of the process? And if so, did they manage?
They did, yes. Yep. So I have only about 10 minutes left of presentation time, so I'm going to go relatively faster through the rest of my presentation. I just want to talk a little bit about what are formal methods. They're basically described as mathematical techniques to, I mean, this is a very general term. It's one of these things like you kind of know it where you see it. My take on it is it's based on math, it's machine checkable, and it's capable of proving properties about code and models, but it's really important to read the fine print. The assumptions could be unreasonable, or the guarantees that the formal methods might be giving you could be too weak to be what you actually care about. There's a whole range of different kinds of formal methods-based tools. So this is a notional graph. The horizontal axis shows kind of how much effort is required to use the formal methods tools / how scalable is it. So at the far left-hand side are things that are completely automated and can scale basically to as much code as we know how to write. Whereas the thing at the right, it takes PhD years and can only scale to thousands of lines of code. Whereas the vertical axis is how strong a guarantee can we get out of this formal methods-based technique. At the bottom, there are things like type safety, where at the top is fully functionally correct. So at the bottom left-hand corner are things like type systems, which we use all the time. Anybody who works in a type language like Java uses that all the time. And at the top right-hand side are interactive theorem provers like Isabelle and Coq. And in the middle, there are things like automatic theorem provers, verified runtime monitoring, sound static analyzers, model checkers, symbolic execution. So there's a whole range of tools, and there's a whole bunch of different kinds of systems that have been, different kinds of properties have been proved about those different kinds of systems using those techniques. So they're all useful. There's no way in which you would say like, we only want this kind of formal methods. You want all of them applied at different levels for different kinds of properties and different kinds of systems. So you might say like, well, what kind of software is actually worth verifying? If you step back and think about it, it would be like those exquisite artifacts from which you can then build much bigger systems where a whole bunch of that bigger system, like you don't really care about. Like for the quadcopter, the unmanned little bird, we didn't verify the camera system. We verified the communication system. We verified the thing that made sure that different partitions were separate from each other. So it's not all software, it's key software. So that kind of key software might include things like a separation kernel, hypervisor, a real-time operating system, a compiler, a garbage collector, file system, web browser, sandbox, crypto algorithms, things like that. And the good news is that for all of those kind of key exquisite artifacts that are the building blocks of bigger systems, all of them have, they're examples of all of those categories that have already been verified to be functionally correct. So some key examples are the SEL4 microkernel. So a microkernel is the core essence of an operating system, the part that absolutely positively has to be run in privileged mode. The SEL4 microkernel is about 10,000 lines of C code. The proof of full functional correctness is about 480,000 lines of proof. It took about 13 person-years to build the proof of correctness and 8 person-years to build the infrastructure to do that. It has the fastest known one-way interprocedural fast path, so it's very performant. So that's the existence of this is what allowed me to make the case to DARPA that formal methods were ready to be tried out on real systems. Then another canonical example is the CompCert verifying C compiler. So this is a verified C compiler that maps from a large fragment of C. It includes almost everything except concurrency down to assembly code and proves that the assembly code correctly implements the source level program. It took 42,000 lines of C and proof. So it was developed inside the Coq theorem prover, and then they extracted the compiler from the theorem prover. And with no optimization, it's faster than GCC. With levels 01 and 02, it's a little bit slower than optimization. It took about 3 person-years to build, but those are 3 person-years of Xavier Lois, who is one of those amazing, amazing people. So probably needs to have a little bit of an expansion factor for a mere mortal who is building the same code. So what are impediments to using formal methods? One of the key impediments is that there just aren't that many people who are experts in formal methods. This survey was from 2009, and it showed that there are less than 5,000 people in 2009 around the world who know how to use formal methods. But this is changing, but it's still not very many people compared to the number of people who are writing code. I see your question, and I will take it as soon as I'm going to talk to yeah, cool. Another is that it takes more effort to both verify the code and write the code. I told you that the SCL4 took 480,000 lines of code, which was like several orders of, 2 orders of magnitude more than the actual code itself. That's a little bit of an outlier. If you look at the rest of the data points on the slide, it's the level of effort is more reasonable, and I would argue is within a reasonable level of overhead for the kind of exquisite artifacts that we're talking about when given the possible negative consequences. And I think the key issue here is that right now the incentives are not properly aligned. The people who pay for bugs in software and the exploits are not the people who develop the code. If we could get those incentives aligned, then the costs associated with the formal methods developments would be considered cheap. It's just that the incentives right now are not aligned so that people don't have to pay the costs at all. The performance is a little bit slower generally, but that's just because it usually takes more time to verify the fastest implementation, because usually the fastest implementation has fast paths. So there's no intrinsic impediment to having the verified code be just as fast as the non-verified implementation. And we're seeing more and more versions deployed into real systems that run fast enough to be used. So, for example, Amazon has replaced, both Amazon and Google have started to use verified versions of crypto algorithms or transport level security implementations they may be slower than the non-verified versions, but are deemed to be fast enough, and the guarantees that come with them are worth the slight performance hit. Another issue is how long it takes in the development cycle. So Facebook has some formal methods tools that are integrated into the development lifecycle so that when a developer checks something in, they have to pass these formal methods tools before they can finish the check-in process. And they get feedback from the formal methods tools within like 10 minutes so that it's within the kind of normal development process. And as soon as Facebook was actually able to incorporate that into the time frame the developer was working, the number of bugs that the formal methods tools that found that the developers actually fixed skyrocketed to super high rates. I'm going to skip that and skip that. So some of the lessons learned is that before you want to use formal methods tools, it's a good idea to eliminate the obvious bugs. And you don't really want to verify all code. You really just want to verify the essential infrastructure and contain the rest. Automation is really important. And we have a ton more that we need to do. We need to increase scaling. We need to increase automation. We need to get buy-in. Like the engineers at Amazon were much more inclined to think about the tools because their colleagues who presented it described it as exhaustively testable pseudocode as opposed to formal methods. And so thinking about how to approach users is really important. And what I would argue is that it's actually within reach where we can use formal methods to verify critical parts of critical systems and build those out of verified components so that we can produce a system that has much higher level of security associated with it. And buggy software will no longer be the easiest attack vector, so that attackers instead will have to switch to more of that phishing or other ones of those attacks and get the software developers off the hook as the easiest attack vector. And Black Hat is reduced to non-scalable attack vectors where he has to physically go and touch the system that he wants to hack. Okay, I'm going to stop there and let you guys ask questions for my last 5 minutes. Sorry I went so fast at the end.
I wanted to ask a question about CompCert and get a better understanding of what it does. Does it make C, does it guarantee that you're using C in a behaviorally defined way? And if so, why not use Rust or another systems programming compatible language that is a little safer?
Yeah, so what it does is it defines the subset of C that is used in the aviation industry, and it 100% defines the semantics of that part of C. And the goal, in fact, so in the aviation industry is very, very different than the automotive industry, right? The automotive industry is kind of the Wild West as far as software quality is concerned. The aviation industry, super high quality standards. The process of getting software approved for an airplane is very, very time consuming. It's described by a very elaborate process that requires human beings to read the assembly code because they don't trust the compiler. They're not going to trust Rust either. And so the goal was to have a tool that could be verified that would map from the C code to the assembly code so that those people could read the C code instead of the assembly code. I think they still haven't actually approved the ComCert toolchain. It's very, very hard to get tools approved for the aviation toolchain. So having a simpler language like C rather than the more complicated language like Rust made that a much easier process. It was also a grand challenge. Like, could you actually verify a compiler? I think one of the interesting things is it turns out a compiler is actually a relatively easy thing to verify. Not that it's easy, but easier than say the microkernel for I think maybe two reasons. One is that the specification is actually pretty straightforward, right? One of the reasons why the code for the proof of the correctness of the microkernel was so big is just writing down what it means for a microkernel to be correct. It's not easy. It takes a lot of specification. Whereas a compiler, it's like, well, the semantics of the assembly correctly implements the semantics of the source code. That we know how to write that down concisely. And the other is that the way a compiler is structured is a series of micro passes. Like you just the one pass, one pass, one pass, one pass. Each one does a simple thing. So you can decompose the proof into a series of very simple passes and just prove each pass is preserving the semantics. So your proof becomes also destructured, whereas the microkernel is this rat's nest of everything touches everything else and all the properties you want to prove are global.
As someone from the other side of the barrier, it is worth noting that nobody writes Rust for embedded code right now. It's just non-existent. And at the time where ComCert was designed, Rust didn't even really exist, I believe. So nobody knows how to write Rust. Rust support for embedded systems is basically non-existent, and right, and it didn't exist at the time. And there's millions of lines of code already out there, right? And some of it has been verified to a very high degree of certainty, but the compiler was still untrusted. So all these things are really, really strong arguments for a C compiler. C is just, it's everywhere, right? It's out there. So there's no really escaping C yet.
Sorry, right. And Greg points out I misspoke about the ComCert doesn't lock down the semantics of C. It just maps whatever C did to the assembly code. So if it was undefined at the C level, it's also undefined at the assembly code level.
Yeah, let's keep the discussion kind of geared towards Kathleen. Are there other questions?
Go, Paul.
Kathleen, I have a question. First of all, thank you so much for this incredibly engaging keynote. I think this is exactly the kind of high-level perspective that we needed at this workshop. Going back to some of your earlier slides about the advances that have kind of made formal methods seem, kind of on the verge of having a much broader impact, I have a question about the role of compute. So to the extent that faster computers have been a key ingredient, is there any role going forward for specialized hardware? Or are we, just going to be taking advantage of CPUs?
Yeah, I actually don't know that I have a good answer to that question. Does anybody else who's a formal methods expert have an opinion? I kind of think that specialized hardware has been useful for machine learning because the problems are so stylized that there are sort of certain idioms that codifying them in hardware has made sense. My feeling about my intuition about the formal methods is that there's much broader variety. And so codifying it in hardware is more challenging. That said, the end of Moore's law means that architects right now are going and designing all sorts of different kinds of hardware. And so the future is specialized hardware for lots and lots of different kinds of applications. So if formal methods researchers could figure out like, oh, we need hardware that does X, then I could imagine that we would indeed see specialized hardware. And then the problem of how do you map high-level problems onto all sorts of specialized hardware is a problem for programming language researchers and compiler researchers. And that's a super hard problem. So like, sure. Yeah, we're all going to need to get together and have lots of research meetings in the future. James, I think your question was next.
Yeah, I was wondering, because living software, of course, is changing constantly. If you verified a given program and then you modify it a small amount, how much of your previous work for verification will hold over?
Yeah, so that's in fact one of the slides I skipped. The answer is it depends on somewhat the kind of the change. It's also, and whether you anticipate it, like whether you allowed for that or not. So this AWS is using is verifying parts of their HMAC. They're basically their transport layer security protocols. And they're constantly wanting to make changes to that code. And so they didn't want to have to re-verify that all the time. And so they set it up so that when a developer made a change to any of those algorithms, the verification code could rerun. And in 12 months, they had to replay the correctness code 956 times. And 953 times the proof went through automatically because the changes were orthogonal to what mattered for the proof. And only 3 times did the proof have to change. So in those 3 times, they had to go call the proof engineer back and say, okay, can you update the proof? So that's one example of setting up a system in such a way that the proof can be automatically updated. It's often the case in these formal methods proofs that there is in fact a script. It's not like you do it by hand interactively all the time. You kind of set up a script that does it. And so the question is whether the script will continue to work as you make the change or not. And it depends on like what kind of a change you made. Did you change something that fundamentally interferes with why the property holds or not? And how you structured the proof in the first place. So I think this is an area where we're just barely starting to get our feet on the ground. I think that it's going to take we're just starting to apply formal methods to practical systems. And so this kind of software engineer, proof engineering question is a relatively new research question. So I would say right now, probably we don't do a very good job at this, but this is something that will become increasingly important in the future.
Thank you.
I had a question. Thanks for it was a great talk. Thank you. When you talked about I guess it was DARPA's efforts to make these drones more secure. I guess you said there was like sort of some amount of time, I forget how, maybe it was 18 months or some fixed amount of time they put into making the system provably secure, and then had the hackers take another go at it. Was there any thought of saying, could the same level of security guarantees been achieved potentially through non per se formal methods approaches, like a more standard just reading the code, or more standard security engineering techniques?
Yeah, we didn't do that kind of assessment. Do I don't know if I have a strong, surely to some extent, but that's the technique that people have been applying for years and has produced no good improvements. So we didn't scientifically measure it, but I'm dubious. Maybe in the context of the DARPA program, where you're paying people to beat the formal methods-based techniques, they would have sufficient motivation to do it. But I think in the real world, it doesn't happen.
All right, thanks.
I have one more question for you, Kathleen. From your perspective as a DARPA program manager and working with specific industries, it sounds like aviation obviously has a very long history and a clear motivation to take a very safety conscious viewpoint. Is there any role for governing bodies in accelerating the adoption across other industries, which are kind of more like the Wild West? And I would describe life sciences and medical devices, and probably more like the automotive industry, rather than aviation, unfortunately.
Yeah, I think that I'm a little bit puzzled why the biomedical is not more like the aviation industry, given that not all of biomedical, but the things like insulin pumps and pacemakers, things that go into a human body that are clearly there have been black hat or white hat hackers who have demonstrated that you can hack an insulin pump wirelessly to change the dose of the medication, or hack a pacemaker, and hacking those in a strategic, you could kill somebody, right? When Cheney had his pacemaker implanted, he had the wireless capability removed from the device because he was concerned about that. So
Okay.
I don't really understand why the federal agencies that are responsible for certifying biomedical devices don't do more. The Federal Highway Transportation Safety Authority is definitely is working towards better standards for automobiles. They're working on a vehicle-to-vehicle and vehicle-to-infrastructure communication standard, and they were starting that just as the HACM's work was coming online.
Yeah,
and so go ahead.
Så egentligen det handlar om att delta i intervjuer. Det finns ett jobb som förberedelsejobb som är.
Is Pablo, are you talking to us or are you talking to somebody else?
Let's see here.
Jag förstår, ja.
Maybe Pablo is talking to somebody else and is just not muted.
Precis.
Gopal, can a host mute Pablo then?
Auditoriet, alltså lyssna på ett seminarium, så Zoom.
Whoever
Så
the host is should be able to mute the person.
Pratar i bakgrunden.
I ought to be able to. I'm not able to for some reason.
You know, I think, I absolutely think that regulatory bodies should be moving in a direction of, I mean, the tension that the companies say is that the kind of the ones that I was putting on the defense contractors, that they don't have the capability, that the capability doesn't exist, that it will delay the time to the product, that it will suppress innovation. Some of those are true and some of those are exaggerated, and some of those may be true and still worth doing because of maybe it's okay if we slow down innovation a little bit in exchange for much higher quality. I think the root of it is if we could get more I think if we could change the software. So the software liability is a really big issue, right? Like if you look at, the software industry liability regime has been like, the software is good for nothing. Like when you install any software, basically you have to, one of the things that you don't read is that this software is good for absolutely no purpose. Versus like the automotive industry, they are held liable for the quality of their product. If there is a defect that is caused by negligence, they're responsible. So as I said at the beginning, automobiles are software on wheels. So which industry's liability regime is going to take precedence in the end? My personal opinion is society is not going to let car companies get away with saying this car is good for nothing. We're going to expect the liability that we've come to expect for cars to continue to hold. And so eventually we're going to get liability for cars that is what it always has been, that if there's software defects in the car that causes, crashes, et cetera, loss of life, the car companies are going to be held responsible. And then if they're being held responsible for their software, why aren't other people being held responsible for the quality of their software? And I think it could be done in thoughtful ways that don't squash innovation, but I think that's coming. And I think when that comes, then the mindset about formal verification and the cost of security is going to change, and software vendors are going to think about tools for improving the quality of their code in a very different light. Things that seem prohibitively expensive in terms of time or cost now are going to seem cheap in the future. And it's not that those costs aren't there now, they're just being paid by somebody else. They're being paid by the consumer, they're being paid by society. And I personally think more of that cost, not all of the cost, but more of it should be paid by the software vendors so that their incentives are aligned to produce better quality software so that the actual costs that everybody's paying go down. That's a whole different talk.
Absolutely, but I think that is one of the key takeaways for us here. And so maybe this is one small step in that direction, and some of these conversations can continue onwards. Thank you so much, Kathleen. So we're at time. So let me go ahead and turn it over to my colleague, Patrick Schultz, who will be introducing our next speaker.
Okay, so it's my pleasure to introduce Gregory Malecha. Gregory is the Director of Formal Methods at BedRock Systems, where he builds formally secured foundations for the software stack. He received his PhD in computer science from Harvard University, doing research on program verification and proof automation. And he's also worked on formal verification of cyber physical systems and stochastic optimization techniques for supply chains. And now he will be telling us about bringing verification to the mainstream, verifying concurrent C++.
Thanks so much for the great introduction. As I said, my name is Gregory Malecha, and I'm going to talk to you about our work at BedRock on verifying this very hard problem of concurrent C++. So I'll just give you a brief idea of what BedRock Systems is so that you have a context for a little bit for the rest of the talk, what our point of view and what it is that we're building. So a lot of what Kathleen mentioned in her talk is something that's very related to what we're working on. You know, BedRock Systems is building a modern trustworthy compute base, which is a virtualization stack for us. And we're taking an approach where, and the reason I guess I'm here is because our approach is to really integrate formal methods from the ground up. And a lot of what I'm going to talk about is the value add you get from applying formal methods before you get to that final QED. The work that we're doing is work in progress. And so, you know, we don't have a full verified stack at this point, but we've already shown a lot of places where getting formal methods in early is actually very beneficial. And we have a very tight collaboration between the FM group and the systems group, you know, working on and looking at and reviewing code early, proposing changes. And we've been seeing the value of that, you know, as we develop the software. So the target of what BedRock Systems is working on, as I mentioned, is a virtualization stack. You might ask, well, what is the specification of a virtualization stack? Kathleen mentioned that, you know, one of the nice things about verifying a compiler is, to some extent, the problem is well defined. You know, you know what the source language is supposed to do, you know what the target language is supposed to do, and you can kind of say, these two things are connected in some way, which is made formal by this notion of refinement. It really says that all behaviors of the implementation are also behaviors of the specification. And that same property holds, the same idea holds very well for a virtualization stack. In the virtualization stack, the implementation language is a piece of ARM hardware. And interestingly, the specification is also a piece of ARM hardware. So in some sense, you might say, well, that's kind of a boring specification. Just don't run your virtualization stack. But it gives us a platform on which to build additional services, things like introspection, which allow us to view and monitor guests, and also consolidation. Kind of these are the standard things that people use virtualization for. And basically getting in at the same level, we're able to provide the interface that you expect. So you can go and run an unmodified Linux or unmodified Windows guest and kind of get a property that says, if there is a bug when I run on the BedRock stack, then there's also a bug not running on the BedRock stack, because I know that the behavior the BedRock stack is showing, you know, was also admitted by the specification, which doesn't involve the BedRock stack. So in some sense, you can't blame us for bugs in your code. And it's a great starting point because we're not saying every line of code has to be verified everywhere. And if you look at the projects that Kathleen was talking about, you see the same sort of thing. Like, they didn't verify every line of code, like things like the camera drivers, but instead they isolated them. And the virtualization approach kind of carries that, that technique through. The BedRock stack is a pretty big system. The blue components are the things that we are actively developing. So it's a capability-based microkernel, Nova, which is open source. On top of that, BedRock Systems is working on a user space, or has developed a user space that allows you to, that provides additional services on top of the microkernel. And on top of that user space, we run various host-level applications, for example, different VMMs, and the virtual Ethernet that you saw in the consolidation slide. And these things run essentially as separate hyperprocesses. And then on top of that, you know, we have oh no, sorry, present. On top of that, we have, we run these unverified guest components, and the setup of the system also allows you to run unverified components at user space level within the host. This is usually done for things like drivers.
I am muted because I'm checking that I don't start talking in the middle of a...
You are not muted anymore.
A meeting.
in addition to writing C++ code, C++ is a complicated language, which we'll talk about.
Yeah, it's a seminar on Zoom and I have.
Excuse me, you are not muted.
See, let me check.
There are also hardware devices that we have to interoperate with. At this low level, we need to worry about the interaction with systems, with serial consoles, page tables, and things like that. So our code goes beyond just straightforward, I guess, C++ code. And there's a lot of interesting and very difficult challenges that arise because of this. I already mentioned that. So I told you a little about who we are, what we do. I'm going to tell you about the idea of why work on verification for C++, and how. I'll talk to you a little bit about the FM value proposition. Predominantly, this is the value proposition before you reach that final QED, which we've had a lot of experience with. The strategy that we use is a technique called separation logic. It's been around for, I want to say, about 15 years now or so. It's, I think, a great system, and I think, well, I'll tell you about why I think it's a great system. And automation is clearly an important aspect. The work we saw in the tutorial yesterday, in the Coq tutorial, understanding the foundations is crucial, but applying destruct for 10,000, 50,000 lines of code is clearly not going to scale. And so we need a way both to alleviate the burden of kind of the boring stuff, so that people can focus on the really interesting problems. All right, so let's start with C++. So when you think about making verification mainstream, where you say, I'm going to start working on a new verification project, the first thing you're obligated to do is figure, what language will you go to use to implement your system? And you really have two choices, kind of. You can pick a better language, and try to convince developers to change their language of choice. Or you can take an existing language and provide tools that work with the idiosyncrasies of kind of languages that already exist. So I'm gonna I know there's a lot of people who are very positive about Rust, and I am very positive about Rust. So don't take anything like this as a ding on Rust. Just want to give you an idea of what you might think about when you think about a better language. So Rust has a great type system. It guarantees a lot of very powerful properties. They're very convenient and eliminate a lot of exploitable bugs. But the Rust type system, I will argue, at least informally, is that it's not powerful enough to prove something as complex as the bare metal property. So just saying the answer to your question is Rust, or the answer to your question is this other tool, it's not going to work. We'll still have to extend the system. And there will be some overhead to that. So we're not going to get this bare metal property for free. So we have to think about how easy is it to extend the system. And another question that I see, and I've heard about it in Rust, I've also heard about it in the context of Haskell and in Coq. Sometimes we find ourselves fighting tools. I've heard stories of people saying, well, I have this simple algorithm, but to get the Rust type checker to accept it, I've got to contort my ideas in some particular way. And it maybe is a little bit more confusing. Rust isn't the only system to blame for this, and maybe you could argue it's not really to blame. But if you think about programming languages like Coq or Haskell, Haskell has a very expressive type system that you can express a lot of really great properties in. Idiomatic Haskell, however, does not say, let's express every property in the type system. And the reason is that the type system does introduce some friction to the ideas that you have. It's kind of like saying, you've got this code and you've got this proof, and somehow you want to put them together so they're nicely and closely connected. But at the same time, the proof might, infect a little bit of the reasoning, make things a little bit less obvious or less idiomatic. If you pick an existing language, you're going to inherit some cruft. Hindsight is 20/20, and decisions have been made over the course of 20, 30 years or so. Often these languages or these systems have no formal description. The C++ standard is about 1,700 pages of text. And it's also an all-at-once sort of complexity problem. Like someone says, we support C++, people say, oh, great, that means you support exceptions and virtual dispatch and virtual inheritance and all sorts of crazy things, which are very useful and might be the actual way that the actual features that you need to support in order to support modern libraries. But tackling this all at once is a very difficult problem. And so the key thing that we focus on is a subset of the language that we can grow over time. We need a mechanism or a strategy by which we can say, right now we kind of support C+, and then, we get the extra plus over the course of years as we, understand the system more, and people say, oh, I really do need this. It's not an option anymore. And that works out in our context predominantly because most of our systems code is kind of like embedded code. So we don't need to rely on exceptions. People prefer not to use exceptions because of costs and things like that to them, runtime costs, et cetera. So the title of the talk gave it away. We picked the existing programming language. And so C++ is our poison. And we need to figure out how do we attack it. And the key thing to note here is that we get to build on top of a lot of work that's been happening for many years. Started before I was in grad school. But the challenges that we see moving from a language like C, which Kathleen mentioned, you have things like ComCert and the verified software toolchain were mentioned on her slides, to C++, you kind of, the differences fall into roughly 3 categories. Surface complexities, things like parsing and type checking are complicated. And generally, we can offload things like this to tools that exist. We choose the Clang compiler infrastructure. And so we rely on the Clang compiler infrastructure to do parsing, type checking, overload resolution, template instantiation, et cetera. So these things kind of get removed from our need to formalize them up front. There are semantic challenges. The primary one that people think about, people who know a lot about C++ think about, is the memory model, which is very complicated. It's crafted in a particular way to allow compilers to do a significant amount of optimization, which tends to be crucial because C++ programs, unlike C programs, tend to be written in a little bit more abstract way, and therefore they rely on the optimizer to do a lot more work than you would in kind of like an idiomatic sort of C style. And the last thing, probably the thing that most people think about when they think of C or C++ is they think of the idea of C with objects. And really, C++ has evolved significantly past that point at this point. But clearly, there are no real C programs that are written these days, or C++ programs written these days, that don't use things like constructors and destructors, inheritance, and things like that. So we need to prioritize the features that we support. And one key thing to note is that C is a very daunting task, but we don't need a complete logic for it. We need a sound logic. So we need a guarantee that if you prove something, then that thing is true, but we don't need a property that says everything that is true is provable. So one particular example of this is the interesting semantics of C++ and C evaluation order for function arguments. And the C standard kind of gives, or the C and C++ standards give kind of very arbitrary, like almost anything can happen, but functions are special, and there's a lot of complexity that goes into that. And we can approximate that whole thing by just saying, parallel evaluation of arguments. And that tends to be easy to express in the setup we have. You can argue like, oh, my program is correct because of these extra caveats in the C++ semantics. But I would argue back, if you have to explain to me why your function call is correct and you're going to go dig into a 1700-page manual, maybe it's better if you just rewrite the function, lift the function call out and rely on the optimizer to do the appropriate thing for you. All right, so now I'm going to jump into the FM value proposition. And really, I'm thinking about this as beyond bug freedom. So we usually think of, verified code is bug-free code. We're done. But this kind of omits all of the design level and compositional aspects that we can get if we pick a good abstraction for reasoning and thinking about our software. So we've got a bunch of examples that I'll talk about, but basically we can think of formal methods as a science of design. I can take 2 designs and put them side by side and write specifications for each of them. You can kind of do something eyeball-y where you count the number of words in each specification, and you'll say, wow, this badly designed piece of code has all these random side conditions, and it's very difficult to check. Whereas this well-designed, well-abstracted piece of code exposes fewer concepts, they're more orthogonal, and they're more natural to use because you don't have to think about all of these kind of arbitrary side conditions. So in a particular example we have of doing this is in the VMM. There's a complicated protocol that we maintain, thinking about the way that virtualization, the way that VMM interacts with the introspection components and mediates access to the guest memory. Now, one thing about whenever you touch guest memory, because one party in this, mainly the guest, is completely unverified, you have no idea what they're supposed to do. You can't put a nice protocol that the guest is involved with. The guest will do what the guest will do. And, we discussed this, over the course of several weeks with, our main VMM developer. And what we came out with is basically a nice specification for this. And the VMM developer actually told us, he said, thinking about the problem in the way we've couched it with these formal methods makes it simpler to understand what is necessary to think about and what is not necessary to think about. And it's providing much more abstraction and encapsulation in the design. And that gives us flexibility to evolve particular components over the course of development without breaking this property, without breaking the arguments here. And I think that's crucial. We've applied this in many other contexts throughout our stack. I can't go into all of them. Unfortunately, I can't show code because it's not public right now, but it'd be great to walk through some of it with people. But all of these things are places where systems engineers developed some code, and we iterated on it with formal methods counterparts. And ultimately, at the end of the day, we've never had an instance where the systems engineers will say, the code you've produced is worse than the code that I originally wrote. It's always been better. And the formal methods kind of shows that when we had tried to specify the original code, the specification was a little bit unwieldy. And we use that to kind of prod them and say, what about this? What about this? What about this? And it's probably hard to hide from a proof assistant asking you random questions like, what about that? What about that? And this really is a way to shine a light on really any problem, any miss in your abstraction kind of is shown out pretty quickly. So you can think about this to some extent as finding code smells before you look at the actual code. It's a design smell, and it's a formal way to look at and couch what is the design and understand, is there something going on there that is maybe awkward? All right, so how do we do this? We pick a language or a logic called separation logic. It's, like I said, been built for a little while, but really it's built for modularity. It has the notion of separation at its core. So it's very modular and it's very expressive. And we need that expressivity to handle the very complicated problems that we're addressing at various points in our stack. So separation logic is our language for formal methods. It's inherent in our understanding, and the idea of separation is inherent in our understanding. The way we build modern software is compositionally, and therefore it should be the cornerstone of our reasoning. The way we think about code should not have to radically change in order to think with formal methods. The core principles of separation logic are a few things. One is that you focus on the state of the system, not the transitions. So avoid thinking about the history and really think about what is true right now. You can embed the history inside the state, but often we find this to be an anti-pattern. Not always, and sometimes it's necessary, but in many cases, it is much more convenient to think about the state right now. And the other piece about this is that we want to describe the whole global state of the system as the combination of a lot of small disjoint resources. And we use this double star, which is actually a star in the literature, to kind of say, these two properties hold, but they hold on disjoint regions of space, disjoint regions of the state. And the nice thing about that property is if I apply an operation to P and it doesn't need to know anything about Q, then Q is preserved kind of obviously. And there's theorems that express this using framing and whatnot. But the idea is that it allows me to give very local specifications to my code. and focus only on the particular resources that are relevant to me. And that gives me a very open world assumption in the proofs that I do. So just to walk through the way this works, and I realize I'm kind of running out of time a little bit. So if you think about a lock, locks are pretty standard abstractions. You might start at the beginning of your program with just some random memory, maybe 8 bytes of memory, and then some resources you would like to protect by that lock. And those are disjoint. This is important. This allows you to call kind of a constructor like mutex, and mutex will say, okay, I'm going to use that memory, and now I'm going to use it as an atomic integer. And I'm going to build an encapsulation boundary around that atomic integer and these protected resources. Now, clients don't have access to those protected resources anymore. They're sealed within the encapsulation of the mutex. So they just think about, oh, I have a mutex. When they call acquire, you can transfer ownership of those protected resources out to the caller. So I don't need to understand how that works exactly, but I just need to know that after acquire returns, I'm going to get access to my protected resources. And at this point, I own it. The mutex doesn't say, I'm going to give you access to these protected resources, but you're only allowed to read them, or you're only allowed to write them, or you're not allowed to free them. Really, this is me. I'm allowed to do whatever I want. And as long as when I call release, I give back protected resources, kind of satisfying the same property, any changes that occur between this call and this call are kind of my own to think about. And so that means that users of these protected resources don't need to know about the existence of the lock at all to talk about the protocol they're allowed to use. And these things are expressed in separation logic specifications, something like this. The mutex has a precondition that the protected resources, that invariant I holds. And at the end, you get that this object points to a mutex. And then to acquire, you say, oh, I've got this mutex. And at the end, you say, okay, you still have the mutex, and you get I. And you also get this assertion that the lock is locked, and the mutex is acquired. And then when you release, you have to give up I, and you give up your locked assertion, and you get your mutex back. So this is a very simple state transition kind of protocol that gives you a lot of flexibility in describing this, relatively complicated thing. At least other ways of describing locks can be pretty complicated. If you say, oh, who owns the resource? And you try to get into that, delegation of resources will become unnatural. And it generally is difficult to work with. All right, so these are the lock specifications that we write. This is essentially code that you would write in Coq for us. And our system kind of interprets these things and assembles the pre and post conditions for us. And then we are able to verify functions like this within the Coq proof assistant. Note that these specifications are directly connected to the code itself, not to some model that is hand constructed based off of the code. And as I mentioned before, both the fact that these things work on a completely open world assumption and that they require only local knowledge about the code to talk about. There's nothing about the protected resources except this notion of I, which in all of these specifications is universally quantified. Locks are not the end of the story for us, somewhat unfortunately, because they're so easy to work with. But we build on top of this very powerful logic called Iris, which is the foundation of a lot of work on modern separation logic. And it has this notion of atomic updates, which is an extremely powerful and compositional mechanism that we've been able to use to do a lot of very nice things. And the Iris developers have used it extensively to verify some very complicated algorithms. And we've been using it at scale and been very impressed by the expressivity and the flexibility that we have with it. So just jumping forward, scaling to the real world, as I mentioned before, proofs can be complicated. You don't want to spend all of your time doing destruct X, destruct Y. And so the key thing around this is automation, and Kathleen touched on this as well. The idea here is to provide customizable automation, such that when you provide a library, you also provide essentially the reasoning principles that you expect people to use to reason about it. And this packaging makes it easy to relate the way that your library should be used in discharging the proof obligations, and to make things more reusable and to avoid the excessive bookkeeping that usually comes about, especially with embedded logics and proof of systems like Coq. And of course, the hard problems don't go away, and we can't just over-focus on the simple ones. I would say 90% of our code is simple problems, but if we focus too much on that, then when we hit the 10% of the code, we'd be stuck and we'd have to revisit our assumptions. But the ability to work in a system like separation logic gives us the ability to address these very complicated problems when we need to, as well as keep the simple stuff simple. So that's the end of my talk. I really appreciate you guys coming, and I'm really happy that I was invited. We are hiring in both formal methods and systems, so you don't have to have a PhD in computer science to join us. You can be a C++ hacker, and if you're here, I assume that you have at least some passing interest in formal methods, and that's a great start to a job at BedRock. So thanks, and I'll take questions. I'm a little over time.
Marcus?
Yeah, so in your proofs, do you assume the hardware is like perfect faultless, or do you have some models for modeling the hardware problems as well?
We assume that the CPU itself is faultless. I think that's a reasonable-ish assumption, or at least it's a simplifying assumption. We do have models of things like hardware devices that under-approximate their behavior quite a bit, like things like a serial Ethernet or serial driver devices and things like that. And it's easier to bake faults into those. Yeah, we basically have to rely on a reasonable model of hardware.
Do you actually bake any faults, like for testing your models or for some other causes? Or your drivers are also faultless in this proving?
I'm not sure what you mean by our drivers are faultless. We verify the code. So we verify the code at the level of the C++ abstraction, and we assume that the code we verify will be faithfully run on the CPU, and we give models of the hardware that we interact with, and ensure that those models we must assume accurately characterize the devices themselves.
Mm-hmm. Okay. Yeah. Thank you.
Sure.
So I'll ask a question. I was wondering what your experience has been with like bringing new developers up to speed, working with the separation logic compared to like learning a new programming language or software.
What is our experience? We've generally had a positive experience. It is not the easiest thing to take someone who is used to programming very low-level C code, interoperating with devices, and then teach them, Coq and a high-level programming language and separation logic. But the courses online for separation logic are very helpful there. Or sorry, the courses online for Coq are very helpful there, and I think there's a difficult challenge of jumping over this hurdle. Like, you're an expert and you're used to kind of knowing what you're doing, and you're kind of being forced into this new domain where it's a little bit difficult and things are done a little bit differently. But we've had very positive experiences, and certainly people with even small amounts of functional programming background have a lot easier ramp up in the formal methods aspects of things. So it's not easy, but it's worth it, I think.
All right. Thank you so much, Greg. And thank you, Patrick, for moderating the session. Let's go ahead and turn it over to our next speaker. I'll give it to my colleague, Jimmy Koppel, who will introduce Hillel Wayne.
Hello, thank you, good Paul. It is my pleasure to introduce our next speaker, Hillel Wayne. Hillel is a professional formal methods teacher and evangelist. He runs Windy Coast Consulting, where his main business is teaching businesses how they can use TLA Plus in comparatively ordinary work, and is the author of Practical TLA Plus, which is perhaps the first formal methods book to have practical in the title. Personally, I first encountered Hillel's work about 3 years ago, and I keep a curated list of the best high-level writing about software engineering, and more of Hillel's blog posts proportionally made this list than any other writer that I surveyed. And so with that, let's give it to Hillel Wayne.
Hi, everyone. Can you hear me?
Yep.
Yes.
Cool. Fun fact, when I first, my first time I gave a talk, I was allowed to give my own speaker bio, but I didn't really have anything interesting to say, so I just listed a bunch of lizard facts, like horned toads can shoot blood out of their eyeballs. It's a defense mechanism. Okay, so I'm going to try sharing the screen so you can see my slides. I'm going to share screen one, share. Can you all see this? Can you all see the slides? Can I get confirmation from somebody that they can see they can now see these slides? Oh, I see that there's chat, which I can't see the chat. Can somebody just say verbally whether they can see the slides?
Yes, we can.
Okay, great, perfect. So, hi everybody. My name is Hillel. I'm going to be talking about designing distributed systems with TLA+, aka everything about distributed systems is terrible, aka waterfall is good, actually. We're going to be talking about what we mean by a DISSIM, why they're so terrible, why a lot of the tools we use don't quite work to fix them, and how TLA+ can help. Not fix it, help. I hate snake oil. Now, before we start, a couple of important things. One, I found out at the last second that I'd misread the agenda, and this isn't a 40-minute slot, it's a 25-minute slot. So I made a lot of changes really quickly that'll hopefully speed things up, and I'll probably talk a bit faster than I'm normally comfortable doing. Hopefully we'll cover everything. If not, I will at some point just say, okay, we're done, and then just like walk away. Second, I've given this talk before, and when I give this talk, I put all of the information as well as questions people asked before at this link, Design Distributed Systems TLA+. You'll also see it at the bottom of the thing if you want to refer to that, so you can use that as a reference. Okay, so also let me know if I'm speaking too fast because I speak pretty fast even for an English speaker. So by distributed system, we usually mean the following properties. People talk about them as applying only to computers. That doesn't work because DISSIMs can also include people or threads or processes. But generally we have multiple agents independently acting, and these again can be processes, threads, computers, where there are some global properties shared by them. So there is some thing we want them all to, as a combined, guarantee. But each one of these agents only has a localized information. That means it doesn't have all the state in its own head and doesn't know what everything else is doing. So we have to somehow allow all these independent things to work together with limited information to generate global properties as an emergent property. Generally, people also talk about one more property of distributed systems called partial failure. It turns out where some of the agents can go down or not work, while the entire thing still has to work globally. This I like to think of as actually a consequence of the other properties of this. So you don't actually need to put this as a fundamental essential thing, but it is a very important consequence. And these by themselves, just multiple agents, global, local, is enough to make distributed systems terrible. Why is that? Because it introduces a couple of things that you normally don't see in smaller programs, one of them being concurrency. Concurrency is the ability for multiple agents to run in different orders. And this leads to what we call state space explosion. Let's take an example, and now I'm going to slow down because I realize I'm now moving even faster than I thought I was. We have some global value, the property we want, which we'll just call X. And this X is a number. We also have two agents that are running. One of them increments X, one doubles. They start at the same time. Each of their actions is atomic. So each one happens in exactly one instant. How many different n values of X can there be? So if you run through this in your head, you'll probably find that there's two possible values. Either we double and then increment, in which case X is 3, or we increment and double, in which case X is 4. However, even if we do either one, there's still an intermediate point where X is 2, but we haven't done the other worker. This means we have 5 distinct states or configurations everything can be in. We also have 2 timelines. One where we go from X1 to X3 and one where we go from X1 to X4. These are called behaviors. So the size of the state space, as we call it, is 5 states, and the size of the behavior space is 2 behaviors. Now, this is a pretty small model. We can keep it all in our heads, but what happens is that as we add more concurrency, the state space gets considerably larger. I'm now going to make a small change to the system. Instead of the agent's operations being atomic, they're now non-atomic. So we can have the first agent set the value of what it's going to change, then the entire first agent runs, and then the second agent actually doubles X. This means it's possible for there to exist race conditions where one agent clobbers the other's information. How many possible states are there now? I'll give you all a minute to think about that. A precious minute I don't have. So instead of 5 states and 2 behaviors, we now have 13 states and 6 behaviors. If we added a third 2-step worker, we could have a maximum of 540 distinct states. So we've gone from potentially 5 distinct states to 13 to 540. This is what we call state space explosion, this being a model of, in this case, an alternating queue. Even small amounts of concurrency create large amounts of intermediate states where different configurations are possible. In other words, by adding concurrency, the number of states can grow fast. And that's why the state space can get really huge really quickly. But we also have to worry about the behavior space. It's not just enough to say that, oh, you can have a lot of different states. We can also have a lot of different timelines. And a key reason for this is a different part of what makes systems hard called non-determinism. Our original model I gave you with the 2 agents, while it was concurrent and globally non-deterministic, it was locally deterministic. Each agent could do exactly one thing at each time. It might have 2 steps, but the steps were always sequential. It turns out this is actually a poor model for how real systems work. Because imagine that you are incrementing a counter. Maybe the user has multiple things they can input. Maybe something can fail. If you have X, you might want to be able to say that we either increment X by 1 or by 2, or the entire thing crashes. And this, like concurrency, can actually make the state space larger, but it can play even more hell with the behavior space. Let's take a new example. We have X starts at 0 as a global thing and 2 concurrent agents. One increments X if it's less than 6, one decrements X if it's greater than 0. The state space is only about 7 states. And if we only look at behaviors that are 5 steps long, there are 16 of them, where a behavior would be something like, can I turn on this pen? Oh, no, I don't actually want the laser pointer. Where sort of we go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Those are different behaviors. Now, let's make a small change to the system. Instead of having incrementing X by 1, we can either increment X by 1 or by 2. So one small change, one non-deterministic addition. We still have the same state space because we still can't have X be any greater than 6. But now, instead of having 16 5-step behaviors, we now have 113 5-step behaviors. We can do, for example, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, etc. So essentially, any path through the state space becomes its own behavior. So while the state space can grow very large, the number of ways that things can go grows even faster. And of course, this is a problem because both states and behaviors can be invalid. States being invalid is pretty intuitive to people. Imagine now this is a database. If we have corrupted data, say something that violates our database constraints, that is an invalid state. But we can also have state behaviors that pass through only valid states, but are invalid behaviors. Consider something like eventual consistency. We want to commit some data, and at some point the data comes into sync. But because desynchronization is a natural part of the system, it's not an invalid state. That means that a path that goes through desynchronization but doesn't resynchronize only goes through valid states, but as a whole is an invalid behavior. So both states and behaviors can be invalid. And this is a problem for distributed systems because even one broken state or one broken behavior is enough to cause a serious problem in production. This is because these systems like to run at scale, and at scale, horrible things happen. Imagine we have an invalid state that only triggers 1 in every billion events. And imagine that this is a very, very small distributed system and only processes 100 events a second. I've worked on dissims that process far more with like 3 engineers. How often will we see this horrible 1 in a billion thing happen? at roughly the same rate that businesses have to file their quarterly taxes every 3 months or so. Or in other words, over a long enough time, a system will do everything. It will see every possible state and will exhibit every possible behavior. We like to refer to this as Murphy's Law. So distributed systems are terrible. People have tried to come up with a lot of systems to make them less terrible. These include things like things that everybody is so ubiquitous that people don't even think about them, like compare and swap in the hardware, things that everybody knows about and uses, like locks and transactions, and things that are on the very cutting edge, like software transactional memory or nurseries. And while these are often very good and help us reduce the state space, they all have a core problem that they all share, and a reason why they are not enough. And the reason is because, as I said, these are all code level things that reduce the size of the state space. We are hoping that by using them, we are removing the invalid states and behaviors. But in order to actually remove the invalid states and behaviors, we have to know where they are in the first place. If the invalid state was here, we haven't removed it. If the invalid behavior is here, we haven't removed that. In other words, code shapes the state space, but it doesn't tell us about the state space. Or code is not designed. State space explosion and behavior space explosion are design problems. Code is not designed. Code can't be designed. Code isn't supposed to be designed. We turn to code to solve these things, though, because code and design have different properties. Specifically, while designing things better would reduce these things, we can't actually test it. If I draw a flowchart for you, if I draw sort of the flowchart and sort of show it to you and say, hey, this doesn't have any bugs, you have no way of knowing if I made a mistake or not. With code, at least, you can test the code to make sure that it is correct. And that's why we sort of prefer code to design solutions. This is also why there's been a large push in more recent years to create designs that are testable, what we call formal specification. This is where we have the ability to specify both the design and the properties in such a way that we can tell whether or not we're actually correct or not. There's a lot of different formal specification tools, and I think a lot of them are very good. I'm going to focus on just one because there's one that's been known to be especially effective with distributed systems and also is shown a lot of effect in actual production systems that are run by real people and not just NASA. This is TLA+, invented by Leslie Lamport, the same guy who also did LaTeX. His idea was that specifying things at the math level would be better at the program level. By this, I mean that if we can talk about the entire system at once, we can talk about things we can't talk about in code. Imagine we're sort of modeling a queue. I want to add to the queue. And the program level, I can say, here's what you should do if this result is a success. Here's what you should do if the result is a failure. But I can't actually say that the result will be a success or failure. That is outside my control. If I'm talking about the whole system at a high level, I can instead say something like, when we try to add, either we add the message, or we fail to add the message, or we accidentally add 2 messages. Holistic system gives us an advantage here. We also have the ability to express entire behavioral properties and state properties. For example, I can say that in every possible state, eventually all the servers will come online. Or I can say in every possible behavior, there's a point where all the servers are online. Because I can specify both states and behaviors, I can talk about what the system should do at a much higher level than I can talk about code tests. And finally, by doing this, I can now apply what's called a model checker, in this case, a tool called TLC, to explore the entire state behavior spaces and see if any of them have bugs. Then if any of them do, it can give me what's called an error trace that shows me exactly how to go from the initial state to the problematic place. Okay, that's pretty cool, I think. But if you follow me at all, like outside of this, you probably know that I'm a huge stickler about examples. I like to find examples that are both good and practical and interesting to people. And a lot of the examples of these tools are kind of, in my opinion, pretty poor. They're either things like, we'll prove Euclid's algorithm, or we will do a simple bit alternating queue, or we will solve a puzzle about crossing a river with a goat, a cabbage, and a boat. Or we're going to verify the entire raft consensus protocol is correct. And that doesn't really give us a space to use this if we're not like PhD level academics. So I want to give you an example of how this could actually be useful in day-to-day work. I'm going to model an ETL system. We have a user that creates an upload. And when we create an upload, we want to transform that into content. We're not saying what kind of upload and what kind of content. It could be turning, say, a markdown file into a news page, or an image into a different image, or a video into a transcription of the video. All we care about is that there's distinct uploads and content. Additionally, the user can delete content, in which case we take down the content in addition to the upload. And finally, the user can edit an upload, which changes the content too. We will say, to make things interesting, that this is non-atomic. You first take down the old content and put up the new content. Now, we also want the system to be scalable, which means that we have to make this asynchronous. Instead of basically having the worker happen immediately after the person, we put a message onto the queue saying what we want to do. This queue we will assume is perfect, completely first in, first out, no drops, no duplications, no reorderings. Every message is delivered exactly once. We're going to specify this logic in TLA Plus and the properties we want and see if that has a bug or not. Before I begin, a couple of very important notes. One, we are specifying things, we're not writing things. Specs are not code. We still have to implement the system correctly, and we still have to test it. This is an augmentation to what we can do. It's not fixing what we can do. We still need to be engineers. Second, I'm writing in a dialect called PlusCal. There's a lot of people who write TLA Plus using a DSL. I'm using PlusCal because it's simple for people starting out. And third, Leslie Lamport is a mathematician, first of all, and he wrote mathematical syntax, not programmatic syntax. People get used to this quickly. You are not taking a tutorial, you are listening to a talk. I changed all the syntax to look like Python. I did not change the structure. I did not change the things, just the keywords. You can see the original specification at this link. Okay, 10 minutes left, let's do this. So first, extensions, model parameters, imports, variables, uploads and content are sets, queue is a list. The next ID is what we're going to use to distinguish pieces of content. When we send a message, we append it to a queue. We define a message as the ID of the upload we want to work on and the action we want to take: create, edit, delete. Now we have two parts of the system, the user and the worker. Normally, we couldn't really specify the user. In a code, we could talk about what they can do. We couldn't sort of say what they will do. In TLA Plus, we just make this an independent process. Now, a user can either create content, edit content, or delete content, but we don't know which they'll do. They might create 5 things, then delete them all, or create something and edit it twice. In other words, they're allowed to do something non-deterministically. We represent this using an either or statement. In this case, the user can either create or edit or delete. The model checker will branch on each time it sees this and try all 3 of them in different universes. For creation, we define an upload as who it's from, the version, because for editing, and the ID of the content to make them distinct. Then we add it to the list of uploads, the set of uploads, and then we send a message saying, hey, we want to create this piece of content. That's all we really need to, and then we increment the ID. So the next piece of content will have ID 2. Delete would work analogously. We don't have to increment the ID, of course, except for the fact that deletion is also non-deterministic. If I upload 5 pieces of content, I can choose which one I want to delete. So we have to say, choose one of the things in the set that you want and delete that. With is also non-deterministic, like either or. We can choose which one we want to act on. Finally, for edit, we do both. We can choose which piece of content we want to edit, so that's non-deterministic, and we also know exactly what the new piece of upload will look like. So what we do is, for an edit, we bump the version number. We don't care how we're changing things, we just care we are changing things. So we say, if the old version was version 1, the new version is version 2, we've done an edit. We then remove the old piece of data from the upload set, add the new piece of edit, and then send a message. And that takes care of the human. We're now done modeling the person and everything they can do. Tyranny of the 25 minutes. Now, time to model the worker. The worker is going to wait for messages, and then it will pop from the queue a message and basically work on it. For working on the code, we want to either, based on the action, create or edit or delete it. But critically, we want to say this is non-atomic. If once a worker starts creating the message, a person can still act while the worker's working. So we use these things called labels that say, hey, another process can now act while we're doing this. So essentially, this receive is also a label. So we basically receive, and then we pop the message. That all happens atomically. And then we basically, before we create or edit or delete, we then allow something else to happen. For upload with, we basically then, in order to select the upload corresponding to the message, we use what's called the choose operator, which finds the corresponding thing in the set. Then for creation, what we do is we simply add the same data of the upload into the content set. Delete works analogously. Editing, which we wanted to make non-atomic for the purpose of this demonstration, we have this happen in 2 steps. First, we save the value of the upload to a local variable. Then we remove the exists from the content, so the current thing. And then in a separate step, we push the new value to the set of content. And again, now we're done. Very small, very simple specification. We now have a specification for the worker and the person. And now we have enough that we can actually go and check things. What time is it? Okay. The cutoff was 11, right?
Go ahead and take a couple of extra minutes if you need. I think we started a few minutes.
Sorry, what do we finish at 11:05?
Yes, that's right. Yeah.
Okay, 11:05, I've got that. So one of the things we can check before we even specify any properties is called comprehensiveness, that we haven't made anything ambiguous, that there's something that no matter what we do, something will happen. So I set in my parameters, I upload this into the model checker and I run it. This is what it looks like to run it. And it gives us an error. This is at the top over here, we have what the error is. At the bottom here, we have the trace, how we get the error. What happens is the user creates an upload, then they delete the upload, then the worker receives the message. It looks for the upload, it cannot find it. This is ambiguous. What's supposed to happen? We don't know. If this is the case, we should probably specify what happens if the content is the upload is missing. So the simplest thing we can do here is simply say that if the upload exists, then you actually upload the content. And if it doesn't exist, you just sort of skip. We're going to simplify it to that. We make the changes to both delete and edit, and now our model works. And we can specify properties now. So for properties, I've talked a bit about both state and behavior properties, and we can do whichever ones we want. Behavior properties, as I talked about, tend to be very complicated and interesting, so I'm going to specify one of those. I'm going to say that for every piece of content, there must exist an upload at the same ID, same version, same uploader. So they must always be in sync. But the thing is that if I basically upload a new piece of content or I delete something, this is now going to be untrue, right? This is only true in the long run. This is true over behaviors, but not states. So I add this thing called always eventually. So we can desync where there exists orphan content. We must eventually bring them back into sync. Now, obviously, because I introduced this spec doesn't satisfy this. You're all smart people. There'd be a trap if I asked you that. But it doesn't do this for an interesting reason. It stutters. What happens is we create an upload, the worker creates the content, we delete the upload, now they're out of sync. There exists content that doesn't correspond to an upload. The worker receives the delete message and is going to delete the content, which would bring things back into sync, and then it crashes. As mentioned, distributed systems always have partial failure. We need to be careful with this and always assume that things can fail. TLA plus, unless you say things cannot fail, we'll assume things can fail at any point. In order to say things cannot fail, we make the process fair. Now things work. And now we know that our model works for one worker. If I wanted to test it with more than one worker in code, I would probably have to write a really complicated test harness that would try to explore every possible state. In TLA plus, if I want to add more workers, I just change the parameter. Instead of saying you have one worker, you say you have two. And it'll explore the entire new state space, which will probably be tens of thousands of extra states. So this is obviously going to fail because otherwise I wouldn't bring it up. How many steps will it take to fail? Give it all a thought. How many steps will it take? How many things have to go wrong in the right order to reach a failure state here? So the answer, in case anybody guessed it, is 15. 15 things have to go wrong in just the right order for us to see an issue. Specifically, what has to happen is we need to create an edit, and then we need to edit it. And then the first worker starts to edit, so it takes down the old content. The user then deletes that piece of upload. So now we need to now they're actually in sync because remember, the worker took down the content as part of the edit. But then when it pushes the edit, we now have the new version up. So we now have version 2 in the content and nothing in the upload. If we add a batch cleaner that just nightly sweeps through the data set and deletes any content that doesn't have a corresponding upload, we no longer have that issue. Instead, we have a 16-step issue following a completely different code path, where what has to happen is you have to create something and then edit it twice and have it received by different workers, one of which will skip it because it sees the upload no longer exists because the other worker took it down already. Then the new worker pushes that back, and we have the upload on version 3 and the content on version 2. Again, I'm moving pretty fast here. Afterwards, you can talk to me if you want a more detailed explanation of this error. In order to fix this, we have to actually write smarter editing logic, where what happens is we check to see if we're going to be pushing a version that is lower than the current upload, and if so, we start over. If we do this, then it works. But interestingly enough, we've now introduced 2 fixes, one of which didn't work, one of which did. Did we need the first fix at all? Did we need the cleaner operation, or can just the smarter edit handle things? If this was code, I probably would be too afraid to change this. I'd have all that extra complexity, which might be unnecessary, because actually finding and determining if removing it would cause a bug would take way too long. In TLA Plus, though, it's like 1 minute to check. And it turns out you actually do need both. If you remove the batch cleaner, you still have the old error trace. So time-wise, we have, I think we've got 4 minutes. So that's really the full demo. Again, I can go into more details if people want after. Now, does this work in practice? We are running low on time, so I'll just do a very brief thing. People sort of thought this has been around for a while. The first real use case in the real world that like was successful was Amazon Web Services, where they found bugs that passed their testing, all of their design review, all of their code review, ended up being 35 steps long. So if you thought 15 steps was bad, it can get so much worse. They said that this probably cut months off their project delivery time. It basically made a huge difference for them. And it actually inspired a lot of people to do this too, because this showed this wasn't just useful for nukes and NASA. I ended up using it too at a small place called eSpark, where we basically made an education app for schools, which ended up being accidentally distributed because it had to talk between our system, Apple's like app manager, and then the school's mobile device manager and the actual people's iPad, had a huge number of errors. Once we started applying formal methods to it though, it ended up finding critical issues that would have taken us months to find and fix. A lot of clients started saying that a lot of schools started appreciating how much things got more robust. So this is like really far from Amazon's use case or NASA's use case, where we were basically just a small startup with 8 engineers. It still saved us tons of time. And that's what convinced me that this stuff was actually useful in a more wider field and got me interested in evangelism and teaching. So we're running low on time. So in conclusion, really quickly, distributed systems are terrible. Specification helps. TLA Plus is neat. It doesn't solve things. It makes things better. I do not sell snake oil. If you're interested in learning more, a couple of places to start. First of all, I wrote a book called Practical TLA Plus. As mentioned, the only thing that has practical publisher requirement. It's beginning level, focused on people who don't actually know any math or like in business, but are just using this for their business. Focuses on practical examples like MapReduce, business workflows, rate limiting. It's out now at is.gd/PTLA+. I'm going to put in the Slacky discount code. The next book, if you're interested, is Specifying Systems by Leslie Lamport. It's the canonical text. It's more intermediate level. It covers all the theory. It covers how this is all supposed to work, why it's all consistent. He also made a video course that's a little bit simpler to get into. It focuses on TLA Plus, not the Plus Cal. And finally, you can just hire me. I do workshops, intense ones. One client said that it was the first time he ever took a corporate workshop. That wasn't a complete waste of time. I have a webpage. Talk to me after. I'll be around. And we are on time. Hell yeah. Thank you. Enjoy the rest of the conference.
All right, thank you so much, Hillel. Why don't we take a few minutes for questions? We'll break from 11:10 to 11:20 and then start our final session.
Wait, I had like another 5 minutes? Man, I could have gone.
Well, we'll take questions now, so.
Okay.
I have a question. It's about specifying the process as fair. So what does it do exactly? What do you achieve by specifying the process as fair?
Short answer. TLA Plus is what's called starter invariant. So at any point, the state transition can transition from a state to itself. What fair basically guarantees is that if a process can eventually make process and transition in a way that doesn't have it just transition to itself, it will eventually make progress and move forward. There's actually two kinds of fairness, weak fairness and strong fairness. Strong fairness is a stronger property that tends to not be like as easy to enforce. Weak fairness is basically the table stakes to have any kind of behavior property make sense. We can specify both. We can specify sub-actions too.
Okay, thanks.
Any other questions? I see some discussion going on in the chat.
Okay, so in the chat, let's see. Also, are we still recording?
Yes.
Okay, let me know when we stop recording so I can talk a bit about off record about something. So I'm looking at the chat to see if there's anything. No, that's a different thing. You're also welcome to shout questions if you want. Is there a way to export state transitions as a Haskell type expression? You can then use it in high algebra. I know several people who do it. You can export the trace in the trace evaluator. And then once you've exported it, you can then obviously translate it. I know a couple of companies that have done that, but they've written sort of custom like bespoke tools. There's no general purpose tool anybody's written. Maybe you can be the first. Yes, besides AWS, are there any public universities? I skimmed over that because I was due to a time crunch, but so one of my favorites actually comes from Elasticsearch, where I believe in version 6. They basically had a version of the Elasticsearch, I think, document like the storage engine where they specified it found a bug, which allowed you to have multiple pieces of content with the same ID. They bumped the version. They basically fixed and bumped the version. 3 months later, somebody reported that they'd seen that they run into that exact bug. And the engineers would be able to ask, oh, are you on version 6.2? And they're like, yeah. And they're like, yeah, we fixed that already. It's on version, go to version 6.3. So not only were they able to fix the bug in advance, they were able to instantly identify why somebody else was seeing the weird thing they were seeing. Other examples that I've seen in the real world, Microsoft used it for Cosmos DB. Cockroach verified large parts of their system with TLA+. I've worked with a number of clients who found it useful. I've also heard a lot of stories from people, who used it for things like protocols and like games or basically Cassandra's clusters. There's a lot of use cases out there. It's actually really cool to see how everybody's been taking advantage of it and the different ways they have been using it. I actually managed to, at one point while consulting, crash an entire project by trying to write out the spec and then asking them a couple of questions where they found out they didn't actually know what they wanted and had to basically go back to the drawing board to figure out the requirements and probably save them a lot of money. Very proud of that one.
All right, any more questions for Hillel? Okay, well, thank you so much, Hillel, and I hope that we'll have more ongoing conversations afterwards in the Gather space. I'm so happy to have with us today Mathew Mirman. Mathew received his bachelor's degrees in mathematics and computer science from Carnegie Mellon, as well as a master's degree from Carnegie Mellon. And he's now doing his PhD at ETH Zurich, where he works on AI from the perspective of programming language theory. And he's going to be speaking to us today about a topic that I suspect will be very relevant to many industries, certainly something that a number of my colleagues at the Broad Institute are interested in, which is the idea of certifiable neural networks. So take it away, Mathew.
Okay, thank you very much. So a little bit more about myself. I'm currently a PhD student in the SRI lab at ETH, working with Martin Vechev. Specifically, I'm part of the Safe Artificial Intelligence Project. Our goal is to ensure that when artificial intelligence systems are used in safety critical systems, we can actually make guarantees about them. So here are some of my collaborators other than my advisor. And some of the papers that we're going to be discussing today that we've published in the last few years are, most importantly, the DiffAI paper about differentiable abstract interpretation, the universal approximation with certified networks paper from published in ICLR 2020, the fast and effective robustness certification paper where we introduced the ERON system published in NeurIPS 2018, and our first paper on this topic, AI2, where we introduced the first certification system for neural networks that scales, published in S&P 2018. So a little bit of a background in case you're not familiar with neural networks or the problem that motivated all of this. Neural networks are basically just functions. They can take any inputs and basically have any outputs, and they're trainable. But most of the time they're built up of affine transformations and ReLUs, and they pretty much have no loops. They're just one straightforward program that always takes the same shape. A few years ago, after we discovered that we could train neural networks very well, and they did a very good job, Goodfellow and a bunch of other guys discovered these were actually very hackable neural networks. You could take a neural network that was designed to classify images of animals, and it was doing a very good job of classifying images of animals. It would take a cat, tell you it's a cat, take a dog, tell you it's a dog. and you give it a picture of a panda, and it tells you it's a panda, and then change every pixel in that picture by an infinitesimal amount so that you can't see the difference. It still looks like a panda, but now the neural network is telling you it's something entirely different with even higher confidence than the original classification of a panda. And this was weird, in addition to being a pretty safety critical issue if you're going to deploy neural networks in like self-driving cars. So a lot of researchers have been focusing on this problem, and so now we'll discuss specifically what they've done. I mean, the first thing that they did was they were looking into what types of vulnerabilities, other than just this FGSM attack where you take this noise vector and you add it to this image. People were working on MILP attacks where you search exhaustively for adversarial attacks. After that, the next step was to try to reduce these vulnerabilities. And most of these systems that reduce the vulnerabilities ended up falling under the umbrella of adversarial training. There you augment the training data with these attack images so that the ground truth that the network is trained on ends up being the actual ground truth that it could see in the worst case. However, all of these have the problem of we don't know if they work 100% of the time, and you need such guarantees in safety critical systems. So my work has been firstly on certifying that a network doesn't have this problem. If we had a network that doesn't have this problem, the first thing that we would need to do is know that it doesn't have this problem. So we introduced the systems AI2 and Iran for certifying that networks are robust. But then we noticed, even if you could certify that it's robust most of the time, most networks either aren't actually completely robust or aren't provably robust. So we introduced the DiffAI training system, which takes a network and produces a certifiable network out of that. And importantly, both of these systems were the first scalable versions of these goals. So before AI2, there were complete verifiers. But because of the size of neural networks, they didn't scale to real world cases. And before DiffAI, there were a couple of examples of these that worked on a couple layer deep networks, but nothing that could be actually deployed in a real world system. So before I can introduce and talk about any of these systems in detail, I want to talk about the actual property that everybody's been focusing on. So for the first few years of adversarial examples, pretty much all of the attacks that were developed fell into the umbrella of the L-infinity adversarial ball attacks. And these attacks, you imagine an image as a very high dimensional vector. And you say all images which are equivalent to it are those which are only an epsilon distance away from that vector in the L-infinity metric. Sometimes people also use the L2 metric. Here, I'm going to mostly be focusing on the L-infinity metric. It suits itself a little bit more for our type of verification. Specifically, we say a net is epsilon robust at a point if it classifies every example in the L-infinity ball around that point X to be the same thing and the correct thing. So first, I'm going to introduce our certification system. So fundamentally, verification, which you guys have, I'm sure, all seen before, the goal is to prove some specific property about our network, which, as it turns out, you can think of as just a program. Specifically, the property that we care about is its epsilon robustness at a point. What people were using before AI2 was complete systems. These complete systems always tell you whether a network is either robust or has an adversarial attack around the point. Now, this is a problem because our networks are huge. So they can be upwards of 1 million neurons and tens of millions of parameters. Traditional verification systems, they scale, but they hadn't really been designed to, at least complete ones hadn't been designed to handle things this large. But abstract interpretation actually gave us a tool with which we could attack this problem. So abstract interpretation says, why do we care about the case where it's not robust? We just want to know if this thing tells us it's robust, that it actually is robust. So it gives us a framework that only tells us something is robust at the expense of not always giving us an answer. Specifically, how it accomplishes this is by over approximation. It looks at the set of possible states that a program can be in, and you produce a geometric shape or some abstract shape that covers the possible states. And for every possible transformation inside of the program, you have an abstract transformation. So using this technique, we've built a few systems starting out with AI2. So AI2 was our first attempt at this. Rather than designing specific transformers or doing anything particularly precise, we applied the general framework of abstract interpretation to neural networks in order to leverage the previously developed abstract domains that were available, since there are a wide range of domains that give you different trade-offs in accuracy and precision for different more common types of operations that you could find in the program. Of course, if you do something a little bit more specific, or you can make this more precise and more efficient by tailoring it specifically to our use case. So our next two systems, DiffAI and Eron, introduce specific transformers. So now a little bit more detail about abstract interpretation and our specific case. In abstract interpretation, you create a domain D of abstract objects. Each abstract object represents a set of possible states. The meaning of represent a set of possible program states is given by the concretization function. And then we have a program which can be broken down into a composition of a set of concrete functions F. And our goal in abstract interpretation is to provide a sound transformer for that individual program piece F. So in a neural network, we have affine transformations and ReLUs predominantly. So if we had a ReLU, which took one set of neurons or n neurons and output n neurons, we would convert that into an abstract ReLU that takes in abstract objects and outputs abstract objects. So in most of this work, we've been focusing on the zonotope domain, which has a couple of nice properties for neural networks that make it really efficient. In particular, it can represent affine transformations perfectly. And it can do this because it itself is essentially an affine transformation. It is a matrix that represents an affine transformation of a k-dimensional cube onto the set of activations of the neural network. So when we try to abstract an affine transformation or a convolution in the neural network, all we have to do is multiply that convolution or that matrix multiplication with the affine transformation of the zonotope. Also, it can represent balls perfectly, which is the robustness property that we want to verify. The only drawback of this is that it cannot represent ReLUs perfectly, and the default transformers that AI2 was using are not necessarily the most ideal things that you can use. So we've developed the ZBox Deep Zono, and later teammates have developed Deep Poly in order to approximate ReLU better. So now I can actually talk a little bit about these specific transformers, not in too much detail though. So here we can see visualizations of these transformers applied to a ReLU. And in this case, you can see in these three graphs, we have the ZBox transformer represented as the blue area, the Deep Zono is the red area, and it's approximating a ReLU of the input line, which is on the horizontal axis assigned to the output neuron on the vertical axis. So the ZBox, what it's doing is it treats the zonotope, or it turns the zonotope into a box If it knows that it cannot do a perfect transformation around the ReLU, so it knows that it can do a perfect transformation if the input values to the ReLU are all positive, because if the input values to the ReLU are all positive, then the ReLU is the identity function. But if the input values to the ReLU straddle 0, we need to do some sort of approximation, because if you can see here, can you see my cursor? No, probably not. You can see here that the ReLU itself, represented as the dashed line, is a nonlinear and non-convex shape if represented perfectly, and our domains can only represent convex shapes. But what we can do in the case that we straddle 0 is convert the zonotope in this dimension essentially to an interval, and then apply the ReLU transformation for interval. I'm not going to go over the interval or box domain in any detail, because it's essentially just interval arithmetic, which is pretty easy to work out on your own. But I will describe the deep zono in a little bit more detail. So what deep zono does is it notices that the Z-box transformer actually loses quite a bit of precision in the case that most of your values in the input domain or in the input dimension are positive. In this case, you can see in the Z-box transformer, there's a lot of wasted space in the blue area that would count as points that aren't realistic in the final output of the neural network, that aren't actually possible, but we need to consider. Deep Zono uses a heuristic where we say, let's try to minimize the area in the input and output plane of the zonotope that we produce with this transformer, and we end up computing the slope of the line between the minimum point of the ReLU in the output and the maximum point of the ReLU in an output, and producing a zonotope shape around that. Given these transformers, we can do much better than our original attempts with AI2, but I think it's worth noting that our original attempts with AI2 were already significantly ahead of what prior systems were capable of. So the original systems were based on SMT solvers. Of course, ReLUs are basically if statements. They include a lot of branching, and the SMT solvers had some heuristics to try to reduce the branching, but still ended up being incredibly slow. So you can see here on a 9-layer deep by 200 neuron wide network, ReLUplex took around 3,000 seconds, which is not usable in a real-time system. Our naive application of abstract interpretation, on the other hand, just took a couple of seconds at most. And this isn't even a real world network. A real world network has hundreds of thousands of neurons, not a couple thousand neurons. At the same time, because ReLUplex was taking so long, we decided to set a timeout, because sometimes you just don't know how long it's going to take. And with that timeout, we were only able to verify a very small, less than 10% of the images for our biggest network here. And with our system, we were able to verify over 60% of the images for our robustness specifications. So it's great that you can certify things, but just being able to certify robustness properties turns out to not be enough. The problem that we have with just certifying robustness properties is that most of our networks aren't naively robust. I mean, people were able to attack them, and because they're able to attack them, we're not going to be able to certify anything. So why are we trying to certify non-robust networks? So after we tried to certify non-robust networks and we got a little bit of them certified, the next step is to certify adversarially trained networks. The problem with this, though, is that just because a network is actually robust and experimentally robust doesn't mean it's very easily provably robust. this is analogous to the case of standard programs, where just because you've written a correct program doesn't mean you've written an easy to verify correct program. Except it's magnified in this case. You can have 0% provable on anything and have the system take many hours to certify it if you don't do anything about that. So our idea with our second work was to try to create networks intentionally with a training system that made them certifiably robust with actual scalable training methods or certification methods. So here our goal, if we formulate our goal as a training goal standard to machine learning, we can actually come up with a method to produce this. So here we say, let's find a set of weights that maximizes the number of inputs that we can certify are epsilon robust. So that allows us to think in terms of SGD. In order to do that, though, of course, we need to design a loss function that lets us express that we want neural networks to be certified. And we also need to be able to differentiate through the certifier. It turns out that most of the certification systems that you would want to use are for the purposes of automatic differentiation, differentiable. Specifically, they're continuous. So take, for example, interval analysis on a neural network. If you take a ReLU, it ends up just being another application of ReLU to 2 vectors instead of 1 vector. If you look at affine transformation, it adds a ReLU and also has another affine transformation. So from our original network of ReLUs and affine transformations, what we've essentially done is create a different network still based on ReLUs and affine transformations. Because the network is based on, the new network is based on ReLUs and affine transformations, we have some reasonable guarantees for machine learning that SGD might do a good job at training it. So when we actually want to apply this system, one of the most important thing to note is that you do not need to use the same system to certify the network and certify the results that you use to train the network. If you have to differentiate through your certification system, if your certification system is slow, your automatic differentiation of the network is going to be significantly slower. So in this case, we use a very precise method for training, and we use the box domain for, or we use a very precise method for certification, and we use the box domain for testing. This allows us to be actually rather efficient. DiffAI is less than twice as slow as standard training in most cases. And using this, we were able to train a rather large residual network with 500,000 neurons and 16 million weights to be provably robust, as opposed to prior systems which were working on fully connected feed-forward networks with at most 2 layers. I can show you the efficacy of our system using the deep zono transformer from Iran. On just 100 images, essentially randomly picked from the testing set, you can see that DiffAI was able to produce a network where 64% of them were verifiable, whereas adversarial training and baseline training were basically able to do nothing. Now this is okay, and this is fairly high in comparison to modern work for CFAR 10, and the standard accuracy on this network is also relatively high. It's in the 80%, and this is because we chose a relatively small epsilon to use. It's roughly 3 out of 255 pixel lumens, or however you'd say that. However, we noticed a problem. Even modern work hasn't improved on this that much using slightly different training techniques. The state of the art says that we can, for this epsilon, get 60% certified robustness roughly and around 80% accuracy, whereas standard training is giving 95% accuracy on CFAR 10. This is a pretty huge gap. It's been a couple of years since DiffAI came out, and it's surprising that it hasn't gotten much better. So this raises some theoretical questions, specifically knowing that there's a universal approximation theorem for standard training. Universal approximation says that for any function, you can find a network which is going to approximate that function to any degree of accuracy that you want. It says something similar about robust training. It says that you can find a robust neural network for any version of the function that you want, but it doesn't say that you can find a provably robust function. Now, we know that neural network verification in general is NP complete, so it's particularly important that we can find neural networks which are certifiable with efficient methods like AI2 and Iran. So our work in ICLR 2020 showed that they provably exist. We came up with a lifting of universal approximation, which shows that you can essentially create neural networks which for any size epsilon prove that it is certifiably robust with the weakest of domains, just with a box domain. And if you can do that with a box domain, you can clearly do it with any more powerful domains. Now, this is good, but it doesn't tell you anything about the size of the network. So we might be creating huge networks which aren't actually certifiable. So in the future, we are working on creating and describing lower and upper bounds on the size, depth, and width of these certifiable networks. So now that we've discussed the properties of just robust training, this doesn't really have that much to say about safe artificial intelligence, because robustness is a very specific property, especially local robustness, that you might not care about because it might be really hard to mount these type of attacks in actual things like self-driving cars. So what we're trying to do now is leave these local robust ball properties and work on global properties of the input. So one of our attempts to do this is by restricting the types of properties that we would want to apply across the entire input. If you talk about ball robustness across the entire input of a neural network, of course, that's not going to work, because if every input to a neural network is robust, then the neural network only has one possible output, which is incorrect. So our attempt here is to try to certify translational or rotational or perturbational invariance for the entire input domain. Now, it sounds really good to certify something over the entire input domain of a neural network, but not every image in the input domain of a neural network is a feasible image. You can see here, like the input domain includes things like cats and dogs, which would be in the ground truth in the training set, and stop signs, but it also includes things like nonsense noise images, because all of those things have values between 0 and 1. So the next thing that we want to do, and this is actually ongoing work that we have a version of this up on archive, is specify what is actually a ground truth thing in a way that we can certify. So in machine learning, typically the way that you specify a data distribution is with a generative model. These are still neural networks, so we can apply similar techniques in order to abstract this set and use generative networks themselves as specifications for classifiers. This sounds really great, but generative models induce a lot of non-convexity, and it's necessary non-convexity. For example, if you take a head flipping back and forth and the set of interpolations between this head, a convex approximation of this would necessarily include the superposition of the two heads flipped back and forth, which is a nonsense image again. We don't want to try to certify properties of nonsense images. We want to certify properties of only realistic ground truth images. So one of the things that we do here is we can say we restrict the types of properties that we're going to specify or to verify to zero-dimensional interpolative specifications, such as head rotation interpolation. So all of these systems are available online and are open source. You can find them on our page. And in conclusion, we created the first scalable certification framework, the first scalable certification training framework, and after that proved the existence of neural networks that were certifiable. And now we are working on leaving the restrictions of local robustness. So thank you.
All right, thank you so much, Matthew. Why don't we go ahead and take a few questions?
This is a question here.
Hello. So I was just wondering if you could say a few words on maybe the relative merits of your sort of abstract interpretation approach to verification and the SMT approach, and also the mixed integer programming approach, which I sort of heard about and was interested in, and maybe anything else that's out there.
Sure. So yeah, the MILP and MIP and SMT approaches are good in the sense that they're complete, in the sense that they'll give you an adversarial example if you there's an adversarial example that exists, but not great in the sense that they take many hours for networks where there are only a few thousand neurons. I think the state of the art is MILP, where you can get maybe a very, very tiny convolutional network, which is okay, but that's nothing compared to the million neuron networks that we're working towards verifying that people actually use in production. If you want high accuracy on your neural networks, you have to use a big neural network. So it's kind of useless to say, let's just restrict the problem to essentially such a small network that we're now back into the why aren't we using a linear classifier space?
Thank you.
Okay. Oh, there's a question here. So traditional questions of sensitivity and specificity. Well, robustness is essentially a question of sensitivity, and for regressive neural networks, that's essentially what the robustness property is about. And in fact, for the stuff that we're doing on network invariance, it actually doesn't make sense to talk about robustness at all as much as sensitivity. When you ask what is the network going to do, if there's a translation, obviously it's not going to give you nothing. It's going to give you a value of how much the network will or the output will change if there's a change in the input. And why is it not more widely used in ML? It's actually quite widely used in ML right now. I think the robustness sessions are like either the second or the first to the third most popular sessions at ICML and NeurIPS now. Last time I was in person at one of these conferences, it was like 200 or 300 papers just on robustness. So any more questions?
Hi, I had posted a question earlier in the context of bounding boxes around where they straddle the zero for the ReLUs. I wonder if you've looked into zonotype bundles. So using not one, but two separate zonotypes. Because they're so efficient, you can basically pretty much carry two instead of one without losing the accuracy.
Yeah, so we have, so in the original AI2 paper, we do talk about what was the name of the domain that we call it? The Cartesian product domain of essentially any other set of domains, which sounds a lot like this. And you can limit the number of zonotopes that you create at once. In further papers, though, we noticed that you don't really, this lets you express more non-convexity. And it turns out that you don't actually need that much non-convexity. And we're not as near to the limit of non-convexity as we thought we were. Goggendiep's deep poly paper like pushed the limit quite a bit further than everybody thought that was possible when people were publishing about the non-convex barriers or the convex barrier to certification. But also for the diff AI, we've implemented a lot of this stuff on the GPU, and the limiting factor there is actually less time and more space. So GPUs are limited to like at most 24 gigabytes of like GPU RAM. And if you can't fit it all in the GPU RAM, the GPU just crashes, or you have to do some very, very low level stuff. And bundles are actually interesting because you can put them in different runs. But I think it mostly boils down to we don't need the non-convexity yet.
Okay.
So for generators, when you're abstracting over generators, you do need non-convexity. But most of what we've found is that even if you're trying to abstract a higher dimensional shape, you immediately lose. The amount of non-convexity is just too much to handle for any reasonable size generator. And if you're trying to do a lower dimensional surface, it's just so much easier to stay a line or stay a box that you don't need zonotopes.
So that was our last speaker for today. I just wanted to thank all of you for being here. I wanted to thank our speakers, Kathleen, Gregory, Hillel, and Mathew, and our tutorial leaders the last 2 days, Phil and Cody, and of course my program committee as well. It's been a real pleasure organizing this workshop, really bringing together an unusual mix of ideas and topics and audience. And as I've said before, I really hope this is just the beginning of a very long journey. Also wanted to acknowledge our sponsors, Google DeepMind, CEA, Leaf Labs, and of course, my home institution, the Broad Institute of MIT and Harvard. Thank you all again for being here. As I've said before, we do have Gather.town running, and I hope I'll see you guys over there for the next hour, and we can continue some of these conversations.